Welcome to the course for Curve Cryptoswap AMM. This course is for advanced Solidity developers who have experience with Foundry. This course assumes that you have knowledge of Curve B1 stable swap. In this course, I'll show you some examples using Python. However, you won't have to know Python to do the exercises or to understand the key concepts. Why take the course? It might give you some ideas for how to build a new type of AMMs. Curve B2 automatically concentrates liquidity using an internal price oracle that keeps track of the exponential moving average of the tokens. So these are some ideas in math that you'll learn by taking this course. Some other motivation might be audit contests and bug bounties that are relevant to Curve B2. Either the smart contract took ideas from Curve B2 or it integrates with Curve B2. In this course, you'll learn the math and the algorithms of Curve B2. Curve B2 is written in Viper, so we'll do a code walkthrough of the Viper contract, and the exercises are written in Foundry. What won't be covered in this course is the advanced math that is used for the calculation of liquidity and swap amounts. All of this math that we'll skip is inside a single library contract that handle these calculations. I'll be your instructor, Taz. So you might be asking, who am I to teach you this course? Well, I've been a software developer for more than a decade, and I've been a smart contract developer for more than 5 years. I also teach about smart contract programming on my YouTube channel, Smart Contract Programmer. And I am the author of the websites Solidity by Example and Viper by Example. To do the exercises or to execute the code examples, first git clone the repo Advanced DeFi 2024. If you're new to GitHub, you can do this by clicking on code, and then copying this URL, and then inside your terminal type git clone, pasting this URL. Now for each DeFi course, there's a README. To navigate to the README, scroll down, and then click on one of these links. For example, here we have a README for Uniswap B2, B3, Curve B1, and Curve B2. Click on it, and this will take you to a README file where all of the relevant links are included. For example, scrolling down, if you want to play around with a graph that is explained in the video, click on this link. If you wanted to play with the Python code that was explained in the video, click on this link, and so on. Furthermore, if you want to take a look at the diagrams that is explained in the video, click on the folder called xcalidraw. Here you'll find a raw file called .xcalidraw. You can open this with the website xcalidraw, or you can open the PNG file. For example, for Curve B2, click on this, and you can see the diagram that is used in the video. And finally, to execute the exercises, you'll need to navigate to a folder called Foundry. Under Test, there are exercises for different protocols. For example, for Curve B2, the folder is split into two parts, exercises and solutions. Exercises will contain the file where you will write your code. And then after writing the code, you can execute the forge test to make sure that the code that you wrote is correct. And if you're having trouble, or maybe you just want to see the solution, then you can go over to the solutions folder and then click on one of the files. Here it will show you the solution. The full version of this course is available on Cyfrin Updraft. Follow the course on Cyfrin Updraft for better tracking, quizzes, prove your knowledge, and join a community of over 50,000 Web3 engineers ready to help you out and answer your questions. Curve B1 is an AMM that is suitable for tokens that are alike. For example, we have the DAI USDC and USDT. They're all stable coins pegged to $1. Compared to Uniswap B2, Curve B1 will usually give you a better trade for tokens that are alike. However, Curve B1 is not built for tokens where the price are usually different. For example, USDC and ETH. USDC is pegged to $1, where the price of ETH currently goes anywhere between $2,000 and $3,000. This was the case until Curve B2. Curve B2s are AMMs that support volatile tokens. So we see over here that we have the token pairs USDC, WBTC, and ETH. Just like in Curve B1, you'll be able to add and remove liquidity in a single token that you specify. For example, in this pool, we have 3 tokens, USDC, WBTC, and ETH. We can specify to add liquidity only in USDC, and then later take out the liquidity only in ETH. This is nothing new. This was the feature that was already there in Curve B1. Okay, now you might have the question, it's nice that Curve B2 supports volatile tokens, but this was already accomplished in Uniswap B2. What makes Curve B2 special compared to Uniswap B2? The answer is Curve B2 algorithmically concentrates liquidity to the exponential moving average that is tracked inside the contract. That was a mouthful, so let's break this down. Concentrated liquidity means that as a liquidity provider, you set a price range, and inside that price range, you're willing to buy and sell tokens. This was a concept introduced by Uniswap v3. For example, inside the ETH USDC pool of Uniswap v3, we can set a price range to add liquidity. Let's say for the higher price range, we set it to 2,452, and the lower price range, we can set it to 2,450. By concentrating liquidity, you'll have the opportunity to earn more swap fees if the market price moves around this price range. However, if the market price goes out of range, then you'll be left with only one of the tokens. For a liquidity provider, the problem with Uniswap v3 is that you'll need to actively manage your liquidity. When the current market price goes out of the price range of your liquidity position, then you'll need to remove liquidity and then reposition your liquidity somewhere close to the market price again. This, of course, will cost you some gas, and in the process, you might also lose some tokens. However, in Curve v2, liquidity is automatically concentrated based on the exponential moving average. Curve v2 has an internal price oracle that keeps track of the exponential moving average of the prices. By being aware of this exponential moving average, Curve v2 can programmatically decide where to concentrate liquidity. And the other big difference between Curve v1 and Curve v2 is the fee structure. In Curve v1, the percentage of swap fee is fixed inside the contract. However, in Curve v2, the percentage of swap fee is dynamic, and this is based on the amount of tokens that are inside the contract. At first glance, Curve v2 AMM equation looks daunting. There are 3 equations that you'll need to understand. But surprisingly, if you understand Curve v1's equation, then it doesn't take much effort to understand Curve v2's equation. So let's start by reviewing Curve v1's equation. Curve v1's equation is a combination of the constant sum and the constant product. Starting with the constant sum, we add all of the token balances, and the total is denoted as D. Next, we add the constant product to this equation. Multiply all of the token balances, and this must be equal to D over n raised to the nth power. Multiply by D to the n minus 1 on the constant sum part of the equation to match the D to the n on the constant product side of the equation. And then add another component to the constant sum part of the equation, which controls the flatness of Curve v1's curve. A is simply just a number, and K0 is a function of the token balances. This function K0 is exactly equal to 1 when all of the token balances are equal to D over n, and the function goes to 0 when any of the token balance goes further away from D to the n. This is the equation of Curve v1. The Curve v2 equation extends the K0 function. We define a new variable called K. Multiply K0 by a new component introduced in Curve v2. Gamma over gamma plus 1 minus K0 raised to the power of 2. Notice that the K0 component from Curve v1 appears in 2 places. This new component that introduces a new variable called gamma and which is being multiplied by K0 is the magic sauce that enables Curve v2's AMM to have concentrated liquidity. And finally, we replace the Curve v1's K0 component with the new component K. And this is the Curve v2's equation. The only difference between Curve v1 and Curve v2 is this extra component called gamma, which is being multiplied by K0. K0 controls how flat the curve is, and gamma controls the concentration of liquidity. On the right is the graph of the constant sum, constant product, and Curve v1. In this video, let's see what the graph of the Curve v2's equation looks like. To begin with, I'll first copy the equation of Curve v1, and then I'll paste it here. Next, we'll modify this K0 parameter. Curve v2 introduces a new component called K, which extends K0. So let's rename this K0 to K, and I'll also do the same for the equation. I'll replace this K0 with a K, and likewise over here. Okay, so now K is equal to K0, and then we multiply this by an expression that involves gamma. This is gamma divided by gamma plus 1 minus K0. And we square this term, raised to the power of 2. We still haven't defined what the parameter gamma is, so let's do that. Gamma will be a number between 0 and 1. In the real world, this gamma is a really small number, so let's also adjust this to a small number. So this is what the Curve v2's equation will look like compared to Curve v1. The graph of the Curve v2 looks more like the constant product curve, more than the graph of Curve v1's equation. Also, looking at the graph of Curve v2, it's not obvious how this enables concentrated liquidity. Another question is, how does this graph handle volatile tokens? In the next video, I'll answer the question how this graph enables concentrated liquidity. And later on in another video, I'll explain about price scales. Price scale is what enables Curve B2 to support volatile tokens. Looking at the graph of Curve B2's equation, it's difficult to see how this curve enables concentrated liquidity. To see that this curve actually concentrates liquidity, we need to see the curve's B2 equation in a different graph. What we'll need to graph is the token amount on the horizontal axis and the price of that token on the vertical axis. In this graph, we'll consider that the Curve B2's AMM has only two tokens. We'll say that there are two tokens, X and Y. On the horizontal axis, we'll plot the amount of token X. On the vertical axis, we'll plot the spot price. The spot price that we'll plot on the vertical axis will be the spot price of token X in terms of token Y. Let's see what we get plotting different AMMs. Scrolling up, let's start with the graph of the constant sum. Constant sum will swap the two tokens in the pool 1 to 1. And for this example, think token X equal to ETH and token Y equal to WETH. Both should be priced the same. And as the amount of ETH increases, we see that the price stays flat at 1. In other words, no matter what the amount of token X is, it will give you back one of the other token. Hence, the price is always equal to 1. Let's see what happens if we graph the price and the token amounts for a constant product AMM. Okay, for a constant product, we see a curve. And we see that when the amount of token X is low, then the price of this token will be high. For example, let's say that token X is ETH. When there are little ETH in the pool, then the price of ETH will be high. And when there are a lot of ETH in the pool, the price will decrease. Next, let's see what graph it will produce when we plot Curve B1. Okay, here's the graph for Curve B1. This is an interesting one. Notice that around here, the price is equal to 1 for Curve B1, and as the amount of token in the pool either increases or decreases, then it starts to look like the constant product. And you can see that it curves over here, and it also curves over here. Okay, and finally, let's take a look at Curve B2. For Curve B2, which is graphed in green, we see something really interesting. It kind of looks like Curve B1, but it also kind of looks like the constant product. In this example, we see that when the token amount is close to over here, the price is close to 1, but the pricing quickly becomes similar to the constant product. And this is how Curve B2 enables concentrated liquidity. What this is doing over here is for a narrow range of tokens, it's pricing the token as equal to 1, and outside of this range, the pricing quickly becomes similar to the constant product. Now, you might be wondering how I was able to plot these graphs. How do you plot the spot price of different AMMs? This will be a topic for another video, which will be included in the footnote. In the previous video, we saw that Curve B2 AMM concentrates liquidity by creating a narrow range where the price of token is equal to 1. As a quick recap, we mapped the amount of token X in the pool on the horizontal axis, and on the vertical axis, we mapped the price of this token. When the amount of token X in the pool is low, then the price of token X is high. As you can see from here, we have the pricing for the constant product AMM, Curve B2 AMM, and Curve B1 AMM. On the other hand, when there are a lot of token X in the pool, then the price of this token decreases, which you can see on the right side of the graph. The price slowly decreases to 0. Furthermore, for Curve B1, there is a wide region where the price of token X is close to 1. However, for Curve B2, there is a narrow range where the price of token X is equal to 1, or close to 1. This is shown in green. The magic sauce that enables Curve B2 to have concentrated liquidity, this is, there's a narrow range where the price of token X is equal to 1, or very close to 1. This magic sauce that enables Curve B1 to have concentrated liquidity is this part of the equation, g squared divided by g plus 1 minus k0 raised to the power 2. And as a quick review, this component is multiplied by two other components called a and k0. A is the amplification parameter that controls how flat the curve is. This is a parameter that comes from Curve B1. And we also have k0, and where k0 for two tokens is defined to be x times y divided by d over 2 raised to the power of 2. So a and k0 are components that are present in Curve B1's equation, which you can see over here. And in Curve B2, this AK0 is multiplied by this new component. To understand what's going on here, in this video, we'll graph this part of the equation. Since it involves K0, where K0 involves two parameters x and y, this component also takes in two parameters. And the output will be another parameter. So we're going to graph this on a 3D graph and try to understand how this component enables concentrated liquidity. What we're going to do on the 3D graph is map the equation g squared divided by g plus 1 minus k0, where k0 takes in two parameters, x and y, and k0 is defined to be x times y divided by d over 2 raised to the power of 2. Since this equation takes in two parameters, x and y, we need another dimension to map the output. Let's call this dimension z. Hence, we can only graph this equation on a 3D graph. X and y for the input, and the z-axis for the output. Furthermore, what we're going to do is map this equation for the points on various AMMs. For example, let's take the points, all of the points x and y that is equal to d over 2 raised to the power of 2. On a 2D graph, this is an equation of the constant product. Now, taking all the points on the constant product, we'll put these x and y into this equation, and then see what it would look like on a 3D graph. Okay, so here it is. Right now you can only see the x dimension and the y dimension since the d dimension is facing towards you. After I show you this equation g of x and y for curve B1 and curve B2, we'll look at what it looks like when we turn the z-axis from facing towards you to facing upwards. And it's no surprise here that when we map all of the points on the constant product and then evaluate this equation, since the output can only be seen on the z-axis, what we get back is a line that looks like the constant product, since we're taking all of the points on the constant product and then evaluating this equation. But right now, we cannot see the z-axis. Okay, next, let's take a look at curve B1. For curve B1, instead of showing you the outputs for g of x and y, here I want to show you the outputs for the equation K0. So this will be a review from curve B1. In the Cyfrin's course for curve B1, I explained that this equation is equal to 1 when both x and y are equal to d over 2. Otherwise, this will decrease to 0. The reason why I want to show you this here is, one, as a review, and also I want to compare with the outputs of the function g. This is curve B1. And again, no surprise. We're taking the points of curve B1 and then evaluating this equation. The output is on the z-axis, but right now the z-axis is facing towards you, so you cannot really see the outputs of z. And lastly, I'll plot g of x of y for all of the points on curve B2. And this is what you get. As a reference, I'll also show the points x, y, z equal to d over 2, and 1. Okay, let's now turn the z-axis so that we can see what's going on with these equations. Now, as you can see from here, you can see some height at the graphs that we've been looking at. And then when I make this flat so that the z-axis is pointing up, and then I'm going to turn this over to the right a little bit. So now what you're seeing is the x-axis is to your right and the y-axis is to your left. And what we can see from here is that first is that the point d over 2, and 1 is right over here. And all of the graph goes through this point. For the points on the constant product, when we evaluate the function g, it's returning a constant value for z. And this is easy to see. Since the points on the constant product are all the points x and y that satisfy x times y equals d over 2 squared, when we plug this x and y into this equation, well, we know that all of the points on the constant product x and y are always equal to d over 2 raised to the power 2. So this function, k0, will always evaluate to 1. G plus 1 minus 1 is always going to be equal to g. So this equation g for the points on the constant product is always equal to 1. Hence, we can see that it is a flat line on the z-axis. How about for curve B1? For curve B1, here in orange, what you're seeing is the equation K0. We're taking all of the points on the curve B1 AMM and then evaluating this equation. Since the z-axis is pointing up, what you're seeing is the output of this function at each point of x and y. And you can see that when the tokens x and y are d over 2, so token x will have d over 2 amounts, and token y will also have d over 2 amounts, the equation k0 evaluates to 1. As the amount of token x and y move further away from d over 2, this orange curve gradually decreases to 0. Now let's examine this component that enables concentrated liquidity in curve B2. This is shown in purple. The behavior of this curve kind of resembles the behavior of the orange curve. When the amount of token x and the amount of token y are equal to d over 2, this equation, G, is equal to 1. And as the amount of token X and token Y move further away from D over 2, it decreases to 0. But here's the difference between Curve B1's K function and Curve B2's G function. What you can see is that the function G decreases to 0 quicker than the function K. We can play around with this lowercase g parameter to see how the function G behaves. If we increase the G parameter, you can see that the purple curve becomes wider, and as we decrease it, the part that is not equal to 0 becomes narrow. And this is how the function g squared over g plus 1 minus k0 raised to the power 2 looks like on a 3D graph. In the next video, I'll summarize what we learned so far. And the goal is for you to understand how this component inside Curve B2's equation enables concentrated liquidity. What you should remember from this video is that this component behaves like the K0 component. The biggest difference is that it decreases to 0 much quicker than K0. Let's do a recap of what we learned so far about Curve B2's equation. The secret sauce that enables concentrated liquidity in Curve B2 is this component called K. This K is actually two parts, K0 and G. K0 is a component that was present in Curve B1's equation. For Curve B2, we multiply this K0 by another component, here I named it G. Next, we looked at the 3D graph for K0 and G. We turned the 3D graph in a way so that the Z-axis will point up, the X-axis will point to the right, and the Y-axis will point to the left. Here, D over 2 represents when both the token balances of X and Y are exactly equal to D over 2. Both in Curve B1 and B2, D has a special meaning. It represents liquidity. For a pool with n tokens, when the pool is perfectly balanced, each token will have D over n tokens. Here we're looking at an example with 2 tokens, hence D over 2. We first looked at the K0 function, and we saw that it peaked at exactly D over 2. At D over 2, it was equal to 1. And as the token balances go further away from D over 2, we saw that this function K0 gradually decreased to 0. We observed a similar behavior for the function G. When the tokens are perfectly balanced, G is equal to 1. As the token balances go further away from this D over 2, this function will gradually decrease. However, it does not decrease to 0. Since K0 will decrease to 0, this function G will decrease to gamma over gamma plus 1 raised to the power of 2. But what I want to highlight here is that the function G has a smaller range where it's close to 1. When the token balances are both close to D over 2, it is equal to 1. However, move a little bit to the right or move a little bit to the left, and it quickly decreases. Compare this with the function K0 where it gradually decreases to 0. Now let's see what happens to K. Remember, this K is the component that is inside Curve B2's equation, and it's defined to be K0 multiplied by G. Actually, to get the graph for K, it's really simple. For each value of X and Y, we take the value of K0, and then we take the value of G. By definition, we multiply this, and the resulting height on the Z-axis is the value for K. We do this for all of the points X and Y on the Curve B2's AMM curve. And again, notice that this component K peaks when both the token balances are exactly equal to D over 2. Similar to the function K0, this function K decreases to 0 as both the token balances go further away from D over 2. However, since K is a multiplication of K0 and G, you can see here that K has a smaller range where it is close to 1 compared to the function G and also to K0. Okay, but how is this function K the secret sauce to concentrated liquidity in Curve B2? Well, what these curves here represent are how much weight to apply to constant sum AMM and constant product AMM. When the graph that you see over here is close to the peak at 1, it means that the resulting AMM will behave more like the constant sum AMM. And when the curves that you see over here are close to 0, it means that the resulting AMM will behave more like the constant product AMM. Let me give you 2 visual examples of Curve B1 and Curve B2. So here we have the graph of the constant sum and the constant product. And let's start with Curve B1. On the bottom, you see the graph of K0. And again, the way to read this graph is when it's close to 1, it behaves more like the constant sum. And when it's close to 0, it behaves more like the constant product AMM. On the top right, we have the graph of Curve B1. The way to visualize this is that we apply a weight to the constant sum AMM. The amount of weight to apply is defined by the graph below. This is the graph for the function k0, and to this we add the constant product. The resulting graph is curve B1 that you can see on the top right. Now, when the token X and token Y balances are exactly equal to d/2, on the bottom it says that we need to apply all of constant sum AMM. So at this point, the resulting curve, curve B1's curve, will behave exactly like the constant sum AMM. And as the token balances go further away from d/2, it will behave more like the constant product AMM. We can visualize curve B2's graph in a similar manner. We first look at the function k. This will tell us how much weight to apply for the constant sum and the constant product AMM. And what you'll notice from the green graph on the bottom is that it has a narrow range where it acts like the constant sum AMM. Otherwise, it behaves more like the constant product AMM. As we sweep through the points of the constant sum, constant product, and then apply the weights that are defined on the bottom, we get a resulting graph for curve B2 on the top right shown in green. And what you'll notice here is that curve B2's graph has a smaller range where it's flat like the constant product compared to curve B1's graph. And finally, I'm going to show you another angle when we're comparing different AMMs. On the horizontal axis, we'll map the token balance. Here it is labeled as X. You can think about this X as being the balance of ETH in an AMM. And on the vertical axis, we map the price of X. For example, the price of ETH. Now, what's interesting is what's going to happen to the price of token X when the token balance of X is exactly equal to d/2 or close to d/2. Let's start with constant sum. The constant sum AMM will swap two tokens 1 to 1. So the price of token X is exactly equal to 1 no matter what the token balance is. For example, let's say that token X is ETH and token Y is WETH. A constant sum AMM with WETH and ETH will swap WETH for ETH or ETH for WETH 1 to 1, no matter what the token balance is. Next, we have the pricing for a constant product. A good example to understand what this graph is doing is think token X equal to ETH again, and for token Y, let's say it's a token like USDC or DAI. As you would expect, when the ETH balance of this pool, let's say ETH USDC, when this ETH balance is low, the price of ETH will be high. On the other hand, when the token balance of ETH is high, this AMM will calculate the price of ETH to be low. And here is the graph of the price for curve B1. For this example, let's again say that token X is ETH, and let's say that token Y is STETH. These tokens have a similar price, so it makes sense to have a curve B1 pool with these two tokens. When the token balance of X, again let's say ETH, is close to d/2, then this AMM will exchange the tokens close to 1 to 1. You can see that when token X balance is close to d/2, the way it is priced is similar to constant sum AMM. It is quoted as close to 1. However, as token X balance goes further away from d/2, it starts to bend. When the token balance is low, the price will rise, and when the token balance is high, the price will fall. This is a behavior that is similar to a constant product AMM. And finally, we have the pricing of curve B2. Notice that for curve B2, it also has a flat region when token X balance is close to d/2. However, outside the narrow range, you can see that it quickly behaves like the constant product AMM. So in summary, the K0 component in curve B1 creates a large region where it acts like the constant sum AMM. However, in curve B2, because this K0 is multiplied by another component called G, it results in a narrow range where it will act like the constant sum AMM. Outside of this range, it will act like the constant product AMM. And that is how the K component in curve B2's equation enables concentrated liquidity. However, notice that this small region where it acts like the constant sum AMM, the price of token X is given as 1 or close to 1. However, this would be a terrible AMM if token X was ETH and token Y was USDC. This basically would mean that when ETH is close to d/2, the AMM will price ETH as equal to 1 USDC. But if you look at curve B2's AMM in production, you'll see that it is doing well. So how is it able to concentrate liquidity when the price of token X should not be equal to 1? For example, for ETH, let's say that the price should be equal to 2000. How does curve B2 AMM concentrate liquidity around the price of 2000? The way curve B2 concentrates liquidity for price other than equal to 1 is by what Curve B2 calls price scale. And this will be a topic for the next video. Price scales are prices of the token relative to the first token. Let's say that there are n coins in a pool. Then for I equal to 0 and less than or equal to n minus 1, we'll define BI to be the balance of token I. And PI will be the price scale of token I. Since price scale is all relative to the first token, PI for the first price scale, PI where I is equal to 0, will always be equal to 1. And then we have what's called a transformed balance of token I. This is simply defined to be BI times PI. BI is the balance of token I, and PI is the price scale of token I. Multiply these two, and we get transformed balance of token I. Let's go through an example of this transformed balance. Let's say that we have a Curve B2 pool with 3 tokens, USDC, WBTC, and ETH. The price scale will be the prices of the other tokens relative to the first token. Here, the first token is USDC, so the price of USDC relative to USDC is always set to 1. Let's say that the price scale of WBTC is 60,000. WBTC is wrapped Bitcoin. You can think about the price of WBTC is close to BTC, Bitcoin. So let's say that the current market price of Bitcoin is $60,000, and let's also say that this price scale over here is close or equal to the market price. And likewise, let's say that the market price of ETH is 2,000, and also inside Curve B2, the price scale is set to 2,000. Again, this price scale 2,000 is relative to USDC. Inside this pool, what it's saying is that 1 ETH is equal to 2,000 USDC, and 1 WBTC is equal to 60,000 USDC. Next, let's move on to the actual balance of tokens. To keep the math simple, let's say that there are 6 million USDC in this pool, 100 WBTC, and 3,000 ETH. Now let's calculate the transform balance of each token. The transform balance is calculated by multiplying the price scale by the actual balance of tokens. So for USDC, we will multiply 1 by 6 million, and we get 6 million. For WBTC, again, we multiply the price scale by the actual balance, 60,000 times 100. We just need to add 2 more zeros to this. So again, we get 6 million. And finally, ETH, multiply price scale by balance. The price scale has 3 zeros, and the balance also has 3 zeros. So multiplication will end up with 6 zeros, and we multiply 2 times 3, and we end up with 6 million again. So far, we looked at price scales and transform balances. We also looked at Curve B2's AMM from another angle. On the horizontal axis, we mapped the amount of tokens, and on the vertical axis, we mapped the price of that token. When we did this, it revealed that Curve B2 has a small region where the price of the token is close to 1. But if you have a pool where one of the tokens has a high volatility in price, let's say like WBTC, and then we pair that with a stablecoin USDC, then you don't want to concentrate your liquidity where the price of this volatile token will be equal to 1, or close to 1. So how does Curve B2 enable concentrated liquidity when you want to concentrate your liquidity other than the price at 1? For example, we have USDC and WBTC, and let's say that the market price of WBTC is 60,000 USDC. How can Curve B2 concentrate liquidity around this price, 60,000, instead of price equal to 1? Well, the answer is price scales and transform balances. The big idea for price scale is that by setting a suitable price scale, we'll be able to concentrate liquidity around this transform token balances. For example, instead of applying the actual token balances to Curve B2's equation, we will apply the transform balances on the Curve B2's equation. When we do this transform balance will be close to D over 2. Remember that for a pool with 2 tokens, D over 2 will represent the amount of tokens for each token when the pool is perfectly balanced. And notice that around this D over 2, liquidity is concentrated. On the other hand, if you use this graph directly with the actual token balances, since in this example the WBTC balance is 100, 100 will be somewhere over here. The price of WBTC is determined by this graph, and it will be somewhere up over here. However, liquidity is concentrated over here. So if you were to use the actual balance, then liquidity will not be concentrated. However, by using this transform balances, we can swap in a small region where the liquidity is concentrated. Let's go through 2 examples. In the first example, we'll swap 1 WBTC to USDC without transform balances. The pricing of WBTC and the amount of USDC that we'll get back for swapping 1 WBTC is defined by this green curve. Again, on the horizontal axis, we map the token balance of WBTC. And on the vertical axis, we'll map the price of WBTC. For a pool with 2 tokens, Curve B2 concentrates liquidity around D/2. Again, this represents the amount of tokens when the pool is perfectly balanced. For a pool with 100 WBTC and 6 million USDC, this D/2 turns out to be 27,985. How did I get this number? Well, I'll show you this in the next video. And let's say that we have 100 WBTC before this 1 WBTC came in. Okay, so I'll just give you the numbers. Amount of token that comes in is 1 WBTC. We're swapping 1 WBTC for some amount of USDC. And then the amount out turns out to be 54,346 USDC. Again, I'll explain in the next video how I got these numbers. What I want you to remember here is that if you were to swap with the actual amount of tokens and then apply Curve B2's equation, the swap doesn't happen around here where liquidity is concentrated. So for putting in 1 WBTC, we get about 54,346 USDC. And for this and the next example, let's just say that the current market price of WBTC is 60,000 USDC. Okay, with that in mind, let's move on to the next example with transformed balances. Okay, this time we swap 1 WBTC to USDC with transformed balances. Again, the graph on the left will determine the price of WBTC. The liquidity is concentrated around here, which is equal to D/2. And this time, instead of using the actual token balances, we'll use the transformed token balances and then apply Curve B2's equation. So let's first ask, what is this D/2? What's the value of D/2? Well, if you scroll back up, we said that D/2 represents the amount of tokens when both of the token balances are exactly equal. In this nice example, it turns out that both the USDC and WBTC transformed balances are both equal to 6 million. The token balances here are equal. So this means that the pool is perfectly balanced. Okay, so going back now, this D/2 is equal to 6 million. This says that the current transformed balance of WBTC is exactly equal to 6 million. So if we were to do some kind of swap, then we're going to get the benefit of concentrated liquidity. And again, I'll just give you the numbers. Amount in is 1 WBTC. Here, this is the actual amount of WBTC that came in. And amount out turns out to be 59,968 USDC. Let's just compare this number. 1 WBTC and we get back 59,968 USDC. This is when we apply Curve B2's equation with the transformed balances. Compare this with when we apply the Curve B2's equation without the transformed balances, the actual token balances. Put in 1 WBTC and we get back 54,346 USDC. So that's a difference of roughly 5,000 USDC. And you can see here, just by looking at the numbers, that with this swap, we get the benefit of concentrated liquidity. What we just did was swap near this D/2. And when we did that, since liquidity is concentrated around here, and the pricing behaves like a constant sum, if we put in 1 WBTC, apply the price scale, and this turns out to be 60,000, and we will get the equivalent amount of USDC, 60,000 USDC. So swap near D/2. Since around here liquidity is concentrated, the transformed amount in will approximately equal the transformed amount out. Since over here Curve B2 behaves like the constant sum. On a constant sum, if you put in 1 token, you're going to get exactly 1 of the other token back. Over here, this is Curve B2 acting like constant sum. In this example, we put in 1 WBTC. 1 WBTC, we need to transform it into the transformed amount in. We'll need to apply the price scale of 60,000. 1 WBTC will be the actual amount of WBTC. Multiply that by the price scale, so 1 times 60,000. And we get the transformed amount in will be 60,000. And since transformed amount in around here is almost equal to transformed amount out, and what we get back is that transformed amount out will also be close to this number, 60,000. The actual amount of transformed amount out, by definition, will be the change in the transformed balance of USDC. This will be the transformed balance of USDC before swapping, and then minusing it with the transformed balance after swapping. The change in the transformed balance of USDC turns out to be change in the actual balance of USDC times the price scale, P0. From this equation, we can approximate the amount of token out when the swap is happening around this d/2. The actual amount of USDC that will come out, by definition, is the change in the actual balance of USDC. Balance of USDC before swapping minus the balance of USDC after swapping. And this is approximately equal to, so we're going to use this part of the equation. And we're going to solve for a change in B0. So taking this 60,000, to get change in B0, we need to divide by P0. Divide this number by P0. Since the price scale of USDC is equal to 1, this is equal to 60,000 divided by 1, which is equal to 60,000. This 60,000 over here represents the transform balance, and this 60,000 over here represents the actual balance of USDC. So the summary here is that we did some simple math, and we said that when we swap around this d/2, amount out should approximately equal to 60,000 USDC. And the actual amount of USDC that we got back is 59,968 USDC. So the reason why we were able to swap one WBTC for this much amount of USDC is because we swapped near d/2. Around d/2, liquidity is concentrated, and the price scale determines where liquidity is concentrated. In the previous video, I gave you an example of swapping WBTC for USDC without transform balances and with transform balances. So I gave you two examples, and in those two examples, I gave you some numbers that I didn't really explain where it came from. For example, we have d/2 over here with 27,985, and for amount out, 54,346. And the same for the other example over here, 6 million and 59,968. The way I calculated these numbers is by running a Python simulation. So in this video, I'll show you how I wrote that Python simulation, and this will be an optional video. The code that we're going to be using in this video is located under the folder notebook, and the file is called Curve Swap Price Scale. This file is meant to be opened with a Jupyter notebook. Later when we open the file, you'll see that the code inside it is written in Python. So if you don't want to execute this code using a Jupyter Lab, you can copy and paste the Python code and then execute it using Python. To run it with a Jupyter Lab, the first step is to run Jupyter Lab. So starting from the project root of this repo, Advanced DeFi 2024, we'll first cd into the folder notebook, cd notebook. And then from here, we'll run the command Jupyter Lab. This will open the Jupyter Labs in a browser and click on Curve Swap Price Scale.ipymb. And this will open a file that looks like this. And inside here, we'll write our Python code. In this example, what we're going to do is simulate a swap with and without price scale. For the example setup, we will swap WBTC to USDC. We'll say that token X is USDC and token Y is WBTC. We also say that the market price of WBTC is equal to 60,000 USDC. And here's what we're going to do. We're going to first define the Curve B2 equation. Next, we have some setups, and then we'll compare the difference of token out with price scale set to 1. This basically means that we're swapping with the actual amount of tokens. And then do the same, calculate the amount of tokens out with a price scale of 1 and 60,000. What you're going to see is that when we calculate the amount of token out with this price scale, effectively we're swapping near where liquidity is concentrated. So we'll get more token out when we swap with the transform balances. Let's begin by defining the Curve B2 functions. First, I'll define the Curve B2 equation. I'll say def, I'll call this f Curve B2. For the parameters, it's going to take in x, y. These are the balances of the tokens in the pool. And then the Curve B2 parameters, a, d, the gamma g, and the price scale, I'll call this p. I'll start by defining the transform balances. These x and y represent the real balance of tokens, so to transform it, we'll need to multiply by the price scale. Let's say x is equal to the actual balance, x, times the price scale, p0. And then y will be equal to the actual balance of token y times the price scale stored at p1. P will be an array of price scales. Next, I'll define the k0 function and the function k. k0 is equal to x times y divided by d/2 raised to the power of 2. And then the k function will be equal to k0 times the component that involves gamma. Gamma divided by gamma plus 1 minus k0. And then raise this to the power of 2. Okay, then on to the Curve B2's equation. You might be accustomed to seeing the curve B2's equation with left side of the equation and right side of the equation. We will move the right side of the equation over to the left side of the equation so that on the right side of the equation, it is equal to 0. And we'll need to do this so that later on we can use some advanced math to solve for curve B2's equation. Say return x times y plus a, this is the amplification factor, times k times d times x plus y. So this is the left side of the equation that you're accustomed to seeing, and then minusing it with the right side of the equation. Minus d over 2 raised to the power 2 plus a times k times d raised to the power 2. Okay, so this is the curve B2's equation. Next, I'm going to create two helper functions so that we'll be able to use an advanced math library and then solve for d given the parameters x, y, a, g, and p. Say def f, I'll call this d, is equal to, the parameter that we're going to be solving must be the first input. So for the first input, I'll put in a d, and then the rest of the parameters, x, y, a, g, and p. And then we simply return, calling the curve B2 function that we defined above, f curve B2, x, y, a, d, g, p. This function f curve B2 and this function fd seems like they're doing the same thing, but you'll see later why this will become useful. Okay, next we'll set up the initial parameters. So let's say that the amplification factor a is equal to 10. The gamma, let's set it to 0.002. And then the initial token balances. X is USDC, so say x0, let's say this is 6 million, 6E6. Y is WBTC, let's call this Y0 and then set it equal to 100. Since for this example, we're going to be swapping one WBTC for some amount of USDC, we already know what the token balance after the swap for WBTC is. Let's call this Y1, and this will be equal to 2Y0, add 1. Okay, on to the first example. Calculate DX with actual balances. So we're going to put in WBTC, which will be token Y, and then we're going to calculate the amount of token X, USDC, that we'll get out. And for this example, we're going to set the price scale equal to 1 and 1. Effectively, when we do that, the price scale over here will be 1 and 1. So effectively, that means we're applying curve B2's equation directly with the actual balance of tokens. And when we do this, you'll see that we're going to be swapping in a region where liquidity is not concentrated. I'll set the price scales. P is equal to 1 and 1. Now, with these parameters, A, G, token balances, and the price scale, what is the value of D? Well, we don't know yet. So to do that, we'll need to call this function and also use the advanced library available in Python to solve for D. So I'll first install a library that will be able to solve for D given these inputs. This library is called Cypy. If you're running this from your terminal, then you'll need to do pip install. If you're doing this from a Jupyter Lab, then you can do $, and then type pip install Cypy. And then execute the command by hitting Ctrl Enter. Next, we'll need to import a function called fsolve from the module Cypy. So from cypy.optimized import fsolve. In Curve B1, it used the Newton's method to solve for D and to also solve for Y, given the other inputs. This function fsolve does something similar, but also applies advanced math so that it works even better than the Newton's method. So we'll use this function fsolve to first solve for D, and then next to solve for X. D is equal to fsolve. The first input will be the function that it's going to call, and the first parameter of this function must be the variable that we want to solve for. For the first part, we want to solve for D. Given these inputs, what is the D that satisfies this curve equation equal to 0? So we'll first call the function fd, and then next comes the initial guess. Initial guess of what the value of D should be. I don't know what it should be, so let's just put it to x0 divided by 2. Half of the token balance of USDC. And then next, we'll need to pass in these arguments as a tuple. So say args is equal to a tuple of values x0, y0, the parameter a, parameter gamma, and the price scale p. And this is how you call the function fsolve. Now let's try executing this code so far. And let's see what we get for the parameter d. So I get an error here. This optimize should be optimize. Let's execute the code again. And we get an array with a single number. This is the value for D that when you put it into this curves equation with the other parameters, it will be equal to 0 or really close to 0. So the value of D will be stored in the first element of this array. Let's try printing out the value for D and D over 2. And we get D is equal to this value, and D over 2 is 27,985. Once we know what D is, we can solve for token balance of X. This token balance will be the new balance given that 1 WBTC came in. We'll reuse some parts of this code, so I'll copy this and then paste it here. And instead of solving for D, we'll solve for the new balance of token X. Given that we put in 1 WBTC, what should be the new balance of token X so that it satisfies Curve's B2's equation? Let's call this X1, and the function that we're going to call is fCurveB2. Notice that the first input is X. So when we call fsolve with this function, it's going to try to solve for X so that this will be equal to 0. fCurveB2. And for the initial guess, I'll just put in D over 2. And for the arguments passed, this will be the new balance of token Y, Y1, the parameter A, the parameter D that we just solved above, the gamma, and the price scale, which is equal to 1 and 1. Execute this to find the new balance of token X. We'll print this out, and we also print the amount of token X that will come out. Print, let's call this DX, is equal to, the amount of token that will come out is the difference of token balances of token X before the swap and after the swap. This is X0 will be the token balance before the swap, and X1 is the new token balance after the swap. Okay, let's try executing this code. So what do we get? We get that for putting in 1 WBTC, we're gonna get roughly 54,346 USDC. Next, we'll do the same thing with price scale set to 1 and 60,000. So I'm gonna copy this code, and then I'll paste it here. Price scale with 60,000. Then adjust the price scale as well over here, 6E6. Here we'll need to recalculate liquidity D since we have a different price scale, 1 and 60,000, which is used as an input over here. And then we'll print out the liquidity and D over 2. Next, we'll solve for the new balance of token X. And here we don't need to change any code. Let's try executing this code. I made a mistake over here. The price scale should be 6E4, 60,000, 6E4. And then let's execute the code again. And we get D over 2 is 6 million. And DX, the amount of USDC that you'll get, is 59,968. So this is the code that I used to calculate the amount of tokens and the liquidity D for the example that I used in the previous video. In the previous video, we looked at how price scale determines where liquidity is concentrated in Curve B2. For example, let's say that inside the Curve B2 pool, there are 2 tokens, USDC and WBTC. The price scales are 1 and 60,000. Let's also say that the WBTC market price is also 60,000 USDC. And when the pool balances are 6 million USDC and 100 WBTC, it turns out that the transform balances of USDC and WBTC both equal 6 million. When we look at the graph for the price of WBTC on the right, the magic number D over 2 that represents the token balances when both the token balances are exactly equal to each other, in this case turns out to be 6 million. Now, of course, the market price of WBTC will not remain 60,000. It will usually go up and down. Next week, it might be 70,000, or next week, it might be 50,000. In this video, I want to go through an example of WBTC market price going to 70,000 USDC and then adjusting the price scale. Where you should pay attention is the balances of the transform balances and D over 2, where liquidity is concentrated. So to begin with, remember that the WBTC market price is 60,000 and D over 2, which represents the center of where liquidity is concentrated, is 6 million. For example, let's say that the WBTC market price has increased from 60,000 to 70,000 USDC. Now, inside this pool of USDC and WBTC and Curve B2, the price scale of WBTC is 60,000. It's still 60,000, while the market price is 70,000. Hence, the liquidity is concentrated around where WBTC is sold for 60,000 USDC. In other words, in the market, the price of WBTC is 70,000, However, on Curve B2, it is selling for 60,000. An arbitrager can take this opportunity to make some profit. For example, let's say that the arbitrager put in 680,000 USDC and then took out 10.7575 and so on WBTC. The way I got these numbers is explained in the previous video. So we'll just move on. Since 680,000 USDC came in, this increased the USDC balance to 6,680,000 USDC. The balance of WBTC decreased to approximately 89.2424 and so on. We can also calculate the transform balances by multiplying the actual balance of tokens with the price scale. For USDC, it is also equal to 6,680,000. For WBTC, we get 5,354,547.2740. On the graph to your right, let's say that this WBTC balance will be somewhere over here. And notice that it is slightly off the region where liquidity is concentrated. Also remember that D/2 represents the transform balances of each token when the pool is perfectly balanced. When the pool is perfectly balanced, we get that both of the transform balances should be 6 million. So let's compare this actual transform balance with the transform balance at equilibrium. Comparing 6 million with the transform balance of USDC, we get plus 680,000. Doing the same for WBTC, we get that the difference between D/2 and the transform balance of WBTC is minus 645,452. Next, let's say that the Curve B2 price scale adjusts to 70,000. And let's see how adjusting the price scale will change the transform balances and also the difference between the transform balance and D/2. Okay, the market price is still 70,000 USDC. However, the price scale of WBTC has updated to 70,000. The balances of the tokens have not changed, so we will have 6,680,000 USDC and 89.2424 WBTC. The transform balance for USDC has not changed, since we're multiplying the actual balance by the price scale 1. However, for WBTC, it will change. We updated the price scale from 60,000 to 70,000. The transform balance of WBTC turns out to be 6,246,971. Now let's see the difference between the transform balance and the balance when the pool is perfectly balanced, D/2. We first need to find out what D/2 is. It turns out that D/2 is 6,463,117. And let's say that this transform balance of WBTC is somewhere over here. Now let's compare the differences of the transform balances with D/2. For USDC, we'll take this number and then minus it with this number. And we get that the difference is plus 216,882. And for WBTC, we get minus 216,145. Let's now compare this number with this number, which represents the difference of transform balance with D/2 before the price scale was updated. So the price scale is still 60,000. What you'll notice here is that the difference over here is minus 645,452. How about over here? It's minus 216,145. I'll just copy these two numbers to the bottom, and then let's compare the numbers. What you can see is that after updating the price scale, this difference has decreased. Over here, the difference between D/2 is minus 645,452. After updating the price scale to 70,000, the difference has decreased to minus 216,145. Okay, but what do these numbers tell us? Well, it tells us how far the transform balance is from the center of where liquidity is concentrated, D/2. When the price scale was at 60,000, we saw that the transform balance was further away from where liquidity is concentrated. After updating the price scale to 70,000, the transform balance got closer to the center of where liquidity is concentrated. And this is what these two numbers tell us. In summary, by changing the price scale, it changes the region where liquidity is concentrated. Here's the equation of Curve B2 for two tokens. When we use this equation, the x and y's are not actual token balances. They are transform balances. To get the transform balances, you will multiply the actual balance of the tokens with the price scales. But what would this equation look like on a graph when we apply the price scales to the actual token balances? So to begin with, let's first graph this Curve B2's equation without a price scale. We can simply accomplish this by setting all of the price scales equal to 1, so that the actual token balances are equal to the transform balances. Over here, I have the parameters for the Curve B2 equation. A, G will be gamma, D will be liquidity, And here I have a parameter called P1. This will be the price scale of token Y. Since the price scale of token X is always equal to 1, we don't need to put it here. So with the price scale of token X equal to 1 and the price scale of token Y also equal to 1, let's see what the graph of curve B2 will look like. Okay, and then here it is. Next, I'm going to change the price scale for token Y, and we'll see how this graph changed. But before we do that, I'm also going to graph the equation for constant sum and constant product. As I change the price scale, it's helpful to see how the graph of the constant sum and the constant product also change. So let's see how the graph of the curve B2 will change as we change the price scale of token Y. Let's increase the price scale of token Y. So starting from 1, as I increase this, I'll increase it all the way up to 4, and then zoom in. You can see that the flat region of curve B2's graph changed. Notice that the flat region of curve B2's graph is aligned with the graph of the constant sum AMM. Let's also find a point on curve B2's graph where the transform balances are exactly equal to each other. Let's begin by tackling a simpler problem. We'll set the price scale equal to 1. And from curve B1, we know that d/2 will represent the token balances when the pool is perfectly balanced. This point will be d/2 and d/2. So this is the point where in curve B1, token balances are exactly equal to each other. How about in curve B2 with transform balances? To answer this question, we can start by looking at the constant sum equation. So the constant sum equation is x plus y equals d. This d is actually equal to d/2 plus d/2. When the token balances of x and y are exactly equal, x will equal d/2 and y will also equal d/2. Okay, how about with transform balances? With transform balances, we will use the same equation, but instead of using the actual token balances, we will use the transform balance. So we will multiply all of the token balances with the price scale. The price scale of token X is 1, so we can leave it untouched. And the price scale of Y in this example is given by P1. And now using this equation, we can solve for the actual token balances, where the transform balances of token X and token Y will be equal to d/2. The point where the transform balance of token X will be equal to d/2 is d/2. When X is equal to d/2, this equation will become, since this will become d/2, this d/2 we can cancel out with this d/2. And solving for Y, we get that the actual token balance of token Y should be equal to, we divide both sides of the equation by the price scale P1, and we get Y is equal to D divided by 2 times the price scale of token Y, P1. So when the transform token balance of token X is d/2, the actual token balance of token Y must be equal to D over 2 times the price scale P1. Let's now see where this point will be on curve B2's graph as we change the price scale. Let's increase the price scale. And this will be the point where the transform balances are exactly equal to each other. With the actual token balances, this will be d/2 for token X and d/2 times the price scale P1 for token Y. Currently, the price scale is set to 4, and this number makes sense. Liquidity D is 10, so d/2 will be 5, and for the actual token balance of token Y, D is 10 divided by 2 times the price scale 4, so this will be 10 divided by 8, which is equal to 1.25. Let's do a quick review of the constant product AMM. What will happen to the graph of the constant product AMM as we increase and decrease liquidity? So to begin with, we have a graph of the constant product AMM in pink with liquidity equal to 5. On top of this, I'll draw another constant product AMM with liquidity also equal to 5. Let's see what happens as we increase the liquidity for the second constant product AMM, shown in green. As we increase the liquidity, you can see that the graph moves in a diagonal direction to the top right of the screen. You also notice that the graph is more flat compared to a constant product AMM with less liquidity. Now let's decrease this liquidity. What you can expect is the opposite behavior. The graph is going to move towards the bottom left of the screen, towards the point xy equal to 0, 0. And you can also notice that the curvature increased. Let's say that we have a constant product AMM and the graph of this constant product AMM is shown on the right. Over time, this pool is going to collect swap fees, so the liquidity will increase. And as the liquidity increases, we can see that this graph moved towards the top right of the screen, and also the graph becomes more flat. From this behavior, we can tell two things. First, we can compare two constant product AMM and immediately tell which one has a higher liquidity. Another thing is we can compare the constant product curve over time and see how much profit it made. As the liquidity increases, the graph is going to move towards the top right of the screen, so we can figure out how much profit it made. Now let's compare this with two graphs of Curve B2 AMM. Here we have two graphs of Curve B2 AMM with different price scales and different value for D. And now just by looking at these two graphs, can you tell which one has a higher liquidity? Unlike the constant product curve, we cannot simply just compare these two graphs. For example, for a graph of the constant product AMM, we can compare the two graphs and conclude that the graph that is to the left of the other graph has a lower liquidity. However, we cannot do the same thing for a graph of Curve B2 AMM to compare their liquidity. For example, comparing the pink and the orange graph, on this part, the pink curve is to the left of the orange curve, but however it intersects over here. In this region, the orange curve is to the left of the pink curve. So there's no trivial way to compare two graphs of Curve B2 AMM to figure out which one has a lower liquidity. The way that Curve B2 quantifies the value of the pool so that two Curve B2 AMMs can be compared is by constructing a constant product curve with the transform balances. This will give the liquidity for a constant product curve. And then we do the same for another Curve B2 AMM that might have a different price scale. We compare these two liquidity that was constructed by the constant product AMM to compare the pool values of two different Curve B2 AMM that might be at a different price scale and also with different value for D. So, for example, let's say that we have the transform balances and we construct a constant product curve. X times Y equals D over 2 raised to the power of 2. Now, note that this X and Y both represent transform balances. We'll come back to this later. This D over 2, for clarity, this is equal to D over 2 times D over 2. Now, at the moment, this token balances represents the transform balances. The transform balances are the actual token balances multiplied by the price scale. The price scale of token X, let's say, is equal to 1. And let's call the price scale of token Y P of Y. And now this token X will be the actual token balance of token X, and this Y will be the actual token balance of token Y. We can divide both sides of the equation by the price scales. For two tokens, we only need to divide the price scale for token Y. Divide both sides of the equation by P over Y, and the P over Y results in the denominator on the right side of the equation. This D over 2 times D over 2 times P of Y will represent the liquidity elsewhere that you're used to seeing with a constant product curve. So when we construct the constant product curve for the graph of this Curve B2 AMM, shown in orange, we get this, and then we do the same for the graph of the Curve B2 AMM, shown in pink, and we get the graphs of two constant product AMM. If we zoom in, we can see that the constant product curve associated with this pink curve has a higher liquidity than the constant product curve associated with this orange curve. So this is how Curve B2 compares different Curve B2 AMMs that might have different price scale and that might also have different values for D. Let's see what happens when we decrease and increase D, and let's also see what happens when we change the price scales around. So if we increase the value for D for the pink curve, we can see that this liquidity associated with this constant product curve also increase. And if we decrease this, the liquidity associated with the constant product curve also decreases. At this point, we can clearly see that the pool value of this pink curve is less than the pool value of this orange curve. Another thing that will affect the pool value of this pink curve is by changing the price scales around. If we increase this, you can see that the pool value also decreases. And if we decrease the price scale, you can see that the pool value also increases. For a pool with n tokens, the pool value is defined to be D divided by n times the price scale of token 0, P0, multiply this by D divided by n, multiplied by the price scale of token 1, and all the way up to the last token. And then this product is taken to the nth root. This equation is used in two ways. The first way is to calculate the amount of liquidity shares to mint to a liquidity provider. The other case is to calculate the pool value with different price scales when the Curve B2 AMM decides to repeg. The transform balance is defined to be the price scale multiplied by the actual token balance, P of I multiplied by X of I. When the transform balances are all equal to each other, they will equal D over N. But does it make sense to measure the value of the pool with this equation? The white paper for the Curve betwee AMM doesn't offer much explanation for how they came up with this equation. So in this video, I'll explain my thoughts on why I think this equation makes sense to measure the value of the pool. The first place we'll start is how this equation is derived. To construct the equation for the pool value, we start with the parameters A, gamma, and the price scales. Given that we know the price scales, we can also calculate the transform balances. Once we know what the transform balances are, we can calculate this special number D using the Curve betwee AMM's equation. To construct the equation for the pool value, we start with the equation of the constant product AMM. On the left side, we will use the transform balances, multiply all of the transform balances, and then on the right side, we'll multiply D over n times. Since the transform balances are multiplication of the actual token balance multiplied by the price scale, let's unpack the transform balances so that we see the actual token balance and the price scales. Next, we're going to bring all of the price scales from the left side of the equation to the right side of the equation. We do this by dividing both sides of the equation with the price scale of the first token. This will bring the price scale P0 over to the right. We do the same for the next token, and then we do this all the way up to the last price scale, P of n-1. And now what we get is an equation that looks like a constant product, but not quite. So let's make a comparison of the equation that we have so far. The constant product equation for n tokens will be multiply all of the token balances, and then this must be equal to L raised to the power of n, where this variable L has a special meaning. It represents the liquidity of a constant product AMM. Now let's compare the two equations. For both equations, on the left side we multiply the token balances. Let's also compare the right side. For the equation for a constant product AMM, this is equal to L raised to the power of n. But for the equation above, we have something more complex. Going back to our constant product AMM equation on the bottom, when we take the nth root of L raised to the power of n, we get L. If we do the same for the equation above, take the nth root, then we get the equation for the pool value defined for Curve betwee AMM. So this equation represents the value L in a constant product AMM. This is how the equation for the pool value in Curve betwee AMM is derived. Okay, but you might have two big questions that took me a long time to find the answer myself. The first question is, why is the pool value constructed from the equation of constant product AMM? Why not start off with the equation of the constant sum AMM, or maybe Curve B1 AMM, or maybe something else? Why does it have to be the equation of constant product AMM? And the other question is, why is the pool value evaluated at this specific point where the transform balances are all equal to D over n? Why not evaluate the value of the pool with the current token balances? Those are two questions that I had, and for the rest of the video, I'll answer those questions. I'll start with the second question, and the first question will be easier to answer after that. Why evaluate the value of the pool when all of the transform balances are equal to D over n? What's so special about this point? Well, since Curve betwee concentrates liquidity, this point represents the center of concentrated liquidity. And concentrated liquidity means that you're making a bet that the token balances will stay around this point. However, when the market price moves away from the center where liquidity is concentrated, now Curve betwee has to make a decision, whether to concentrate liquidity at a new price scale or keep it the same. And to make this decision, what's important is not the current token balances, but where the center of liquidity is. Curve betwee AMM is trying to decide whether this current token balance will over time go back to the current center of where liquidity is concentrated, or if the current balance is going to stay around the new center where liquidity is going to be concentrated. So what it's trying to compare is not the pool value with the current token balances, but the pool value if the current token balances were to come back to the center of where liquidity is concentrated. And that is why the pool value is evaluated at the equilibrium, where liquidity is concentrated. Okay, how about the first question? Why is the pool value constructed from the equation of constant product AMM? Well, I'm sure there are other ways to measure the pool value, but let's start with what we know. At equilibrium, the curve for the constant sum AMM, the curve for the Curve betwee AMM, and the curve for the constant product AMM all intersect at this point. So to measure the pool value, we have at least two equations that we can use, the constant sum and the constant product. So why not use the equation for constant sum to measure the pool value? Well, the problem with using the constant sum equation to calculate the pool value is that it's not so obvious how to compare the liquidity of a constant sum AMM at different price scales. For example, if I gave you a graph of two constant sum AMMs at different price scales, can you tell me which constant sum AMM has higher liquidity? Probably not. Okay, how about for constant product? Well, the answer is pretty easy. The curve with a higher liquidity will be to the right and above the other one. So for a constant product AMM, it's easy to compare their liquidities. So that is one of the reasons why I think that the equation for the constant product AMM was used to construct the pool value for curve B2 AMM. And in practice, the value for gamma is a really small number. When gamma is small, the curve for curve B2 AMM will look more like the constant product AMM compared to the constant sum AMM. And this is true for different price scales. So these are the two reasons why that I think that the pool value for curve B2 AMM is derived starting from the constant product AMM equation. Curve B2 concentrates liquidity, but when the market price moves away from the center of where liquidity is concentrated, curve B2 makes a decision, either to repeg the price scale or to keep it the same. This decision depends on whether curve B2 has collected enough profit from swap fees so that it can cover the loss from repeg or not. In this video, I'm going to graphically show you how curve B2 makes a loss when it repegs the price scale. In other words, when it repegs where it concentrates liquidity. So let's say that we have a graph of curve B2 AMM with price scale equal to 2. It's going to be helpful to see the constant sum associated with this curve and also the point of equilibrium, where the transform balances of each tokens are equal to each other. We'll also graph the constant product that is associated with this curve B2 AMM. This constant product curve is what's used by curve B2 AMM to compare two different curve B2 AMMs at different price scales. Okay, so let's say that there was a swap, token Y went out and token X came in. And let's say that after the swap, the token balances can be represented as here. And let's say that the price scale, if curve B2 was to concentrate liquidity over here, is given by this straight line in green. Now in practice, curve B2 will not repeg to the spot price. It will make a decision based on the exponential moving average of the prices. So realistically, if it was to repeg to another price scale, it will be a price scale that is in between the current price scale and the price scale at this spot price. But for simplicity, let's say that curve B2 is going to repeg to this price scale shown in green. So to do this, I'm going to draw another copy of the curve B2 AMM at the current state. And I'll do the same for the constant sum associated with this curve and the constant product. And I'll also highlight the point where the transform balances are exactly equal to each other. Now, if curve B2 was to repeg where it concentrates liquidity, it'll have to update this price scale. So let's match this price scale to the new price scale that is shown by this green line. Now the price scale of this green line is equal to the price scale of this pink line. Now, for this example, we swapped token X and token Y went out. Curve B2 keeps swap fees on token out. So realistically, the actual amount of tokens will be slightly above this curve. So let's say it's over here. All of token X came in, but some of token Y was kept as swap fees. So let's say that the point is over here. The next thing that curve B2 does is calculate D so that this pink curve will go through this green point. This represents the actual token balances. So given the actual token balances and all of the curve B2 parameters, including the price scale, it's going to solve for D so that it satisfies the curve B2's equation. On the graph, we can simulate this by moving this D value around until it intersects this green point. Okay, I think this is good enough. And now let's compare the two constant product curves associated with the curve B2's graphs. From here, we can see that the constant product curve associated with the pink curve has less liquidity than the constant product curve associated with the orange curve. And this is what I meant that curve B2 makes a loss when it repegs to a different price scale. There's another way to visualize how a curve B2 AMM makes a loss when it repegs to a different price scale. But before we get started, let me first explain where we left off in the previous video. So in the previous video, we started with this curve B2's AMM graph shown in orange, and the token balance after the swap is shown in green. In this example, we said that token X came in and token Y went out. Curve B2 collects swap fees from token out. So realistically, the token balance will be somewhere over here. And now if curve B2 was to repeg to this price scale, what we did was we first matched the price scale. And we did this by making the green line and the pink line parallel to each other. Furthermore, the new Curve B2 AMM's graph, shown in pink, must go through this green dot, which represents the current token balance. So we adjusted the D parameter so that this pink curve goes through this green point. So that is where we left off in the previous video. And I said that we can compare the pool values of these two different Curve B2 AMMs at different price scales by looking at the constant product curve. We also saw that after repegging, the pool value decreased. We concluded this by comparing the two constant product curves. The constant product curve after repegging, shown in pink, has a smaller liquidity than the liquidity of the constant product curve, shown in orange. But there's also another way to visualize that when a repeg happens, it will make some loss. So to see this, I'm going to first remove the constant product curves. Now we have the two graphs of the Curve B2 AMMs at different price scales and also showing the different equilibrium point. So let's say that a repeg happens, and this is shown in pink. And to show you that after repegging, this pool value has decreased, what I'm going to show you is that there's no way for this green point to come back to this point over here while still moving along this pink graph. This will show you that there's no way to get some of the tokens, hence the AMM has made a loss. So let's say that our token balance is over here. And let's say that a swap happens so that token Y will come in and token X will go out. So this green point will move along this pink curve, and let's see what happens over here. Let's imagine that the token X at this point is equal for both the green point and for the orange point. If the token X balance is 5 over here, then the token X balance over here is also 5. How about the token Y balance? Well, actually, here's the exact numbers. So token X for both this pink curve and this orange curve are equal to 5. How about the balance of token Y? For the pink curve, the token Y balance is 2.12. Compare this with the token Y balance on the orange curve, which is equal to 2.5. When we compare these 2 points, we can see that on this pink curve, there's no way for the AMM to get back 2.5 token Y while also having token X balance equal to 5. So this is another way to see that how Curve B2 AMMs make a loss when they repeg. And the only way for the token Y balance to be equal to 2.5 while the token X balance is equal to 5, the only way is to increase the liquidity D for this pink curve. We can do this by increasing this D1, and what you'll see is that the pink curve intersects with this orange point, which means that this AMM described by the pink curve is now possible to have a token balance of 5 and 2.5. So now the actual token balance can also be equal to 5 and 2.5. However, the only way that we can reach this point is by increasing the liquidity for the pink curve. And the only way to increase the liquidity for the pink curve is either to collect a lot of swap fees or to have liquidity providers deposit more tokens. In this video, I'll give you a high-level overview of Curve B2 contracts. Actually, there is only one contract for Curve B2 AMM. In theory, we can create a Curve B2 pool with arbitrary amount of tokens. However, in practice, Curve B2 pools are gas optimized for either 3 tokens or 2 tokens. The contract that we'll do a cold walkthrough for is called Curve Crypto Optimized WEF. This contract is an AMM for 3 tokens, USDC, WBTC, and ETH. Now, if you wanted a Curve B2 AMM with separate sets of tokens, for example, instead of putting USDC, let's say DAI, WBTC, and ETH, then you will need to deploy another Curve B2 contract that will hold DAI, WBTC, and ETH. As a user, you can do 3 things with this Curve B2 contract. The functions that the users can call are called exchange to swap tokens, add liquidity to add liquidity, and there are 2 functions, remove liquidity and remove liquidity 1 coin. The difference between remove liquidity and remove liquidity 1 coin is that remove liquidity will remove all 3 tokens. Remove liquidity 1 coin, the liquidity provider can choose one of the tokens from the tokens in the pool to remove all of their liquidity in. We'll start our cold walkthrough of the Curve Crypto Optimized WEF contract by looking at state variables. A lot of state variables in this contract are packed when they are stored and unpacked when they are needed for some kind of computation. For example, here we have a state variable called packed precisions. Precisions in Curve B2 is the same as precisions in Curve B1. It stores some numbers so that all of the token balances will be normalized to have 18 decimals. Since this contract holds 3 tokens, this state variable packs 3 of the precisions for each token into a single state variable. into uint256. The reason why different values are packed into a single state variable of type uint256 is to save gas. For example, for this token, we have 3 precisions, and if we were to store this in 3 separate state variables, it would take up roughly 3 times more gas than storing it inside a single state variable. So that's the reason why state variables are packed in this contract. So we have some state variables that are packed. Packed precisions, price scale packed, last price is packed, and going further down, this initial A gamma and future A gamma is also a packed state variable. Let's look at some functions that are used to pack these state variables and to unpack them. Let's start by looking at the internal function called pack. In the comments, it says it packs 3 integers with value less than 10 to the 18 into a uint256. And the code is pretty simple. It's just using some bitwise operators to store 3 values into a single uint256. For the input, it's going to take in an array with 3 elements of type uint256. Each value will be less than or equal to 10 to the 18. The first value will be stored by shifting the uint256 by 128 bits to the left. The next value is stored by shifting uint256 by 64 bits to the left. And the last value is simply stored. What's happening here is that we have 256 bits, which represent a uint256. Starting from the left and going right with zeros and ones, we first have 128 bits, which will store the value for x0. The next 64 bits will store x1, and the last 64 bits will store x2. So that's the function pack. Okay, but where is it used? For example, let's take a look at where it's being used. Here it's being used to pack 3 parameters that are used for calculating the dynamic fee: new mid fee, new alt fee, and new fee gamma. So this is how the data is packed. Next, let's take a look at how to unpack this data. The function is called unpack. It's going to take in a single uint256 named packed, and it will unpack, so it will return an array of uint256 having the size 3. To get the value stored in the first 128 bits, so we're referring to here, to get this value, x0, what we'll need to do is shift this packed value by 128 bits to the right. And then we do a bitwise mask. This number looks mysterious, but I checked and it turns out to be 2 to the 64 minus 1. The next value, so the middle value, which will be 64 bits, and it's going to store the value x1, we can get this by shifting the packed value by 64 to the right, and then again applying the bitwise mask of 2 to the 64 minus 1. And then the last value is simply just appended to the last 64 bits, so we can just apply the bitwise mask to get the last value. So that completes the function unpack. There are 2 other functions that I want to explain here. The functions are pack prices and unpack prices. Basically, they do the same thing as the functions that we just discussed, pack and unpack. However, for the functions pack prices and unpack prices, there's a little bit more logic involved. These functions will pack and unpack the price scales that are used for the transform balances. I personally think that the function unpack prices is easier to understand, so let's first look at the code for the function unpack prices. For the input, it's going to take in the pack prices, and again, here pack prices will represent the price scales that are packed into a single uint256 state variable. The first thing to note is that it's going to return a uint256 array of size 2. There are 3 tokens in this contract, so why is it not returning 3 price scales? Instead, it's only returning 2 price scales. Well, if you think about it, the answer is pretty simple. The price scale of coin 0, the first token, is always going to be equal to 1. So there's no need to store this price scale. So what's going to be returned for the first element in this array is the price scale of coin 1, and the second element of this array will be the price scale of coin 2. Okay, let's take a look at the function body. First, it initializes a uint256 array of size n coins minus 1. This contract holds 3 coins, so this n coins will be equal to 3. 3 minus 1 is 2. So it initializes an array of size 2, and then it copies the value of pack prices into uint256. And next, it runs a for loop. The for loop will run from k equals to 0 to k less than n coins minus 1. N coins minus 1 is again equal to 2, so this for loop will run for k equal to 0 and k equal to 1. Okay, let's take a look at next part of the code. Inside the for loop, it says unpack prices of k is equal to pack prices and price mask. The price mask constant is defined in the top of the code. I copied it over here so that it'll be easier to understand what's going on here. So price mask turns out to be 2 to the price size minus 1. And the price size is defined to be a constant of 256 divided by n coins minus 1. Again, n coins minus 1 is equal to 2. So this is 256 divided by 2, which is equal to 128. Okay, so now going back to this price mask, this is 2 to the 128 minus 1. So what this is doing here, it's creating a sequence of all ones having the length 128. Basically, it's creating a 128 bits mask. The first element of unpacked prices for k equal to 0 will store packed prices and price mask. Packed prices is a UN256, so it can be split into two 128 bits. For the first iteration, it's going to apply the 128 bit mask to the right side of the 128 bits, and then get the value and then store it into here. The next line of code prepares for the next iteration of the for loop. It's going to take this packed prices, and then it's going to do a bitwise shift of 128 bits to the right. So this means that this part of the code will be removed, and then we're left with 128 bits. So now packed prices is equal to the left side of the 128 bits. And then the next iteration, now packed prices equal to this. It's going to apply a price mask again, and then store it into the array unpacked prices for k equal to 1. So that's the for loop, and what we end up with is this. Starting with the UN256 unpacked prices, it was 128 bits and 128 bits. On the first iteration, we stored the right part of the 128 bits into unpacked prices of 0. And for the next iteration, it's going to store this left side of 128 bits into the array unpacked prices at index 1. So that's the function unpacked prices. Let's now take a look at the function packed prices. The function packed prices does the reverse of the function unpacked prices. It takes an array of UN256 of size n coins minus 1, this is equal to 2, and it's going to return a single UN256. What we're doing here is we're packing this array of UN256 of size 2 into a single UN256. First, it initializes some variables, and then moving on, it executes some code inside the for loop. And inside the for loop, it uses some constants, price size and price mask. These are constants that are defined at the top of the code, and to help us understand what's going on here, I've copied the exact code from the top of the code to here. Okay, so let's take a look at what happens inside the for loop. The for loop runs from k equals to 0 to n coins minus 1. So here, think about n coins minus 1 equal to 2, since this contract has 3 tokens. For the first iteration, it bit shifts the variable called packed prices to the left by price size, where price size we said is equal to 128. Since packed prices is initialized to 0, by shifting the value 0 to the left by 128 bits, we still get a 0 back. And to this, we store the value that is stored in prices to pack at the index n coins minus 2 minus k. Okay, so what's going on over here? The easiest way to understand is just go through the for loop and see what value this produces. For k equals to 0 and for n coins equal to 3, this turns out to be 3 minus 2 minus k. And for k equals to 0, we plug in 0 over here and we get 3 minus 2, which is equal to 1. For k equals to 1, we plug in 1 over here and we get 3 minus 2 minus 1, which is equal to 0. So these are the value of the index that is referred over here. For the first iteration, for k equals to 0, the index that we're accessing is 1 from the array prices to pack. And then for the next iteration, it's going to access the value stored in prices to pack at index 0. So for the first iteration where k equals to 0, it's going to get the value for prices to pack at index 1, and then it's going to assign this to a variable called p, check that p is less than price mask, and then adds this to the value packed prices. Currently the packed prices is equal to 0, so this will simply be equal to p, which is equal to prices of 1. And then for the next iteration, it's going to move this packed prices to the left by 128 bits. In the previous iteration, we stored p, and this will take up max 128 bits. So we shift this value to the left by 128 bits, and then get the value for prices of 0. Check that prices of 0 is again less than price mask, and then appends this prices of 0 to packed prices. So that's the for loop, and what we end up with is the first 128 bits will store prices of 1, and the last 128 bits will store prices of 0. So that's the function packed prices. The parameter a and gamma inside the curve B2's equation controls how flat the graph of curve B2 AMM is. The parameter a is from curve B1. In curve B2, it introduces another parameter called gamma, which controls the wideness of where liquidity is concentrated. These parameters can only be set by the admin of this contract. And when the admin sets either the new A parameter or the gamma parameter, it doesn't take effect immediately. Instead, it changes to the new A and the gamma parameter over time. The update will be made in a linear fashion. Here I have a simple graph of how the A parameter will change. So let's say that at time t0, the A parameter was at A0, and we schedule at some further future in time, t1, for the A parameter to be A1. Then over time, it's going to make a linear progression from A0 towards A1. If the current block timestamp is somewhere over here, then the current A parameter will be somewhere between A0 and A1. In this graph, it will be over here. It's a linear progression from A0 to A1 over the time period t0 to t1. So let's take a look at this function. First, it assigns some state variables to a local variable, t1 and a gamma 1. This will represent the future a and the gamma parameter, and t1 will be the future timestamp, where the future a and the gamma parameter will be equal to a1 and gamma 1, which was scheduled by the admin. This future a gamma is actually a packed state variable. The first 128 bits will pack the parameter for a, and the next 128 bits will pack the parameter for gamma. So that is the logic that you're seeing over here. To get gamma, since it's on the right side of the 128 bits of UN256, this gamma parameter is unpacked by doing a bitwise mask with 128 bits. The A parameter is on the left side of the 128 bits, so to get this value, we'll need to bit shift by 128 to the right. If the current block.timestamp is less than t1, where t1 is the future A gamma time, then we know that the current block.timestamp is somewhere between t0 and t1, so you'll need to do a linear calculation to figure out where the A parameter and the gamma parameter is. So to begin with, we first need to get the A0 parameter and the timestamp t0. This is what's happening here. Initial A gamma is also a packed state variable, where A will be packed into the first 128 bits and gamma will be packed into the last 128 bits. Okay, so scrolling down. First, it minuses t0 from t1 and sets t0 to be equal to the current timestamp minus t0. What's happening here is basically we're sliding all of the timestamp by t0 and then sets t2 to be equal to t1 minus t0. This part of the code was a little bit confusing for me, so I'm going to unwrap what's going on over here. So on this line of code, it's saying t1 from the current value of t1 minus t0. So currently, t1 will be equal to t1 minus t0. And then t0 is equal to block.timestamp minus t0. So t0 will be equal to, here I denote it as b for block.timestamp, minus t0. Okay, and what's t2? t2 is equal to t1 minus t0. That's the code that you see over here. And let's unpack this part. We know that t1 was assigned to be t1 minus t0. So that's what you see over here. And t0 was assigned to be b minus t0. So that is what you see over here. Simplify this equation, and the t0s will cancel out and we're left with the original t1 minus the current timestamp. Okay, let's go further down. And here's the part that calculates the current A parameter and the gamma parameter, and it's applying a linear equation to figure out where this value will be between A0 and A1, and also between gamma 0 and gamma 1. As I said earlier, A gamma 0 packs state variables. A is packed as the first 128 bits, and gamma is packed as the last 128 bits. So to get the A0 parameter, it bit shifts by 128 to the right. And the same goes for gamma 1. We see over here that since gamma 1 is the last 128 bits, it does a bitwise mask with 128 bits to get the value of gamma. And the rest of the code is similar. We multiply by t2 plus a1 times t0 divided by t1. The code on the bottom is similar. t2 multiplied by gamma 1 times t0 divided by t1. So I'm going to explain this part of the code, and you also understand this part of the code since they're basically the same logic with different values. Here it's dealing with a0 and a1, and over here it's dealing with gamma 0 and gamma 1. Otherwise, the rest of the code are the same. What it's basically doing is taking a weighted average between a0 and a1, where the weights are defined by the time elapsed since t0. And this is where this part of the code will become useful. So first it multiplies a0 by t2. And we said over here that t2 is equal to the original t1 minus b. Graphically, what would that look like? t1 will be over here and the current timestamp b will be over here. So T1 minus B will be the distance between T1 and B. Okay, so going back down, this part of the code is multiplying A0 by T1 minus B. And how about the next part of the code? It's multiplying A1 by T0, where T0 is equal to the current blocked out timestamp B minus the original T0. And this is what we get. How about graphically? What does it look like? B minus T0 will be the distance from B to T0. Okay, so going back down again. And then it's being divided by the whole duration, T1 minus T0. So if you look at this part of the equation, we have T1 minus B, and then we'll need to divide this by T1 minus T0. T1 minus T0. As the current timestamp B approaches T1, this whole value will be equal to 0. And the simple way to think about it is B is going to make a linear progression from T0 to T1. And at time T1, T1 minus T1 will be equal to 0. So this A0 part will be equal to 0. And then we have this part. So this part is B minus T0 divided by T1 minus T0. When the current timestamp B is equal to T0, we see that B minus T0 is equal to 0. So the weight to apply to A1 is equal to 0. And when the current timestamp B is equal to T1, this will be T1 minus T0 divided by T1 minus T0. So this will evaluate to 1. And we get that this part of the expression will be equal to 1. So this will be A1 times 1. And how about this part? When blocked out timestamp is equal to T1, this part will be equal to 0. So this will be equal to 0. So we're left with A1. So in summary, what we see here is that when blocked out timestamp is equal to T0, this expression evaluates to A0. And when blocked out timestamp is equal to T1, we see that this expression evaluates to A1. So that is how the current A parameter gradually moves from A0 to A1. And this is the same for gamma 0 and gamma 1 as well. The way the current gamma is calculated is the same logic. And that is how the current A parameter and the gamma parameter is calculated. The function that sets the future A and the gamma parameter is called ramp A gamma. It takes in 3 inputs, future A, future gamma, and future time, where the current A and the gamma parameter will be equal to future A and future gamma. You can see over here that it checks that message.sender is the admin that is stored in the factory contract. We can see from here that this function can only be called by an authorized account. There's a lot of checks in this code and I won't go through all of them. The part that I want to highlight is the part where the state variables initial A gamma and future A gamma are set. So after it does some initial checks, it gets the current A gamma parameter by calling the function A gamma. Next, scrolling down, we can see that it does some checks, and then afterwards it sets initial A gamma, the state variable, to the initial A gamma that was calculated above, and initial A gamma time to be blocked out timestamp. Next, it sets the state variable future A gamma and future A gamma time. So that's the function ramp A gamma. Now, after the admin sets a future A gamma, they might want to stop the update. That's when they would call the function stop ramp A gamma. This function can only be called by the admin of the factory contract. Again, it gets the current A gamma, and then sets both the initial A gamma and future A gamma to the current values. So that's the function stop ramp A gamma. The function get virtual price is used to calculate the value of one LP token. When liquidity providers add liquidity, LP tokens are minted to this user. This function get virtual price will calculate the value of one LP token. In Curve V1, virtual price is calculated by calculating D and then dividing by the total supply. Here, total supply will be the total supply of LP tokens that are minted. In Curve V2, it's a little bit different. We take the value for D and then pass it to a function called getXCP. Basically, what the function getXCP will do is calculate the L in a constant product AMM. For example, if we have a constant product x times y equals L square, then this function getXCP will calculate this value for L. Let's say there are n tokens, x0, and then we multiply this all the way up to the last token. Let's say x to the n minus 1. The constant product equation will be multiply all of the token balances from x0 to x to the n minus 1, and this must be equal to L raised to the power of n, since there are n tokens. Now to calculate L, we will take the n in fruit. Now, instead of using the actual token balances to calculate this value for L, what the function getXCP will do is use the token balances when the transform balances will all be equal to each other. So as a review, let's say that the transform balances x sub I are all equal to d over n. Actually, I'll put a tick over here to indicate that this is a transform balance. This will mean that the actual token balance, let's say x sub I, to get the transform balance, we need to multiply this by the price scale of this token. Let's call this p of I, and this must be equal to d over n. The I that you see over here will range from 0 to n minus 1. From this equation, the actual amount of tokens when the transform balances are all equal to d over n will be x sub I equal to d over n times p of I. From this equation, I divide both sides by the price scale p of I, and the p of I comes to the denominator on the right side of the equation. So what get xcp will do is multiply all of this x sub i's, so x sub 0 times x sub 1 times 2 all the way up to x sub n minus 1, and this will be equal to, the first one has a price scale of 1, so it will be equal to d over n. The next one will be d divided by n times the price scale of token 1, and then the next one will be d divided by n times the price scale of token 2, and so on all the way up to the last token, d divided by n times the price scale of n minus 1. Once this is calculated, it will take the nth root of this number to get the value for L. So that's what the function getXCP will do. Let's take a look at this function. Okay, here's the function getXCP. First, it initializes an array of UN256 having the size n coins. Let's say that the pool contract holds 3 tokens. Then this will be an array of size 3. What this array is going to hold is the balance of tokens when the transform balances are all equal to each other. So x sub 0 will be d divided by n times the price scale of token 0. Since the price scale of token 0 is equal to 1, you can think about this as being equal to d over n. And the next element will be d divided by n times the price scale of token 1. And for a pool with 3 tokens, the last element will be d divided by n times the price scale of token 2. So the next line, you can see that x0 is being assigned d divided by n coins, which is what we see over here. Next, it gets the packed prices, which is a state variable that packs the price scales. And then inside the for loop, what you're seeing over here is basically this part of the code. The for loop will range from I equals to 1 less than n coins. N coins, let's say, is 3. So the for loop will range from I equals to 1 to I equals to 2. And you can see over here that it multiplies d by 10 to the 18 divided by n coins, and then unpacking the price scale for token 9. The next line of code prepares for the next iteration. It bit shifts the packed prices by price size. When n coins is equal to 3, this price size turns out to be 128. And after the for loop, what we end up with are the arrays x storing these values. And then, moving on, it passes this array of size 3 to a math function called geometric mean. What this function will do is multiply all of the elements, x0, x1, and x2, and then take the cube root. Here is the first exercise for price scales. The exercise is located under test, curve B2 exercises, curve B2 price scale.test.sol. Okay, let's scroll down and see what the exercise is. The exercise is to calculate the transform balances. For this exercise, we're going to be using the Curve Crypto pool with USDC, WBTC, and WEF. Okay, so with that said, the first exercise is to calculate the transform balances. Let's go over the solution. The transform balance is calculated by multiplying the balance of the token by the price scale, and then it's multiplied by precisions, and then divide by this constant called precisions, so that all of the transform token balances will have 18 decimals. The first token in the pool has a price scale set to 1. So the logic to handle the transform balance for the first token is a little bit different. So let's say XP of 0. This is equal to the token balance of USDC. We can query this by calling pool.balances of token 0. USDC has 6 decimals, so to have the transform balance have 18 decimals, this will be multiplied by precisions. This is precisions of 0. Okay, so this is a transform balance for token 0 for USDC. We have 2 other tokens, WBTC and WEF. So let's run a for loop for uint256. Let's call this I equal to 1. we'll loop it 2 times. So while I is less than 3, I++, we'll first get the balance of this token, uint 256, let's call this bal equal to pool.balances of I. Next, we'll get the price scale, uint 256, let's call this p is equal to pool.price scale. The price scale is offset by 1. So to get the price scale of token 1, you'll need to say 1 minus 1. And to get the price scale of token 2, you'll need to say 2 minus 1. And inside this for loop, you'll say that by saying I minus 1. Okay, let's now store the transform balance into the array xp. xp of I is equal to bal multiplied by the price scale multiplied by the precisions of I. And since the price scale has 18 decimals, we'll need to remove this 18 decimals by dividing by precisions. Okay, so that completes the first exercise. Let's try executing the test. To execute the test, I'm gonna execute this command, forge test, and here's the important part. You need to specify that the EVM version is equal to Cancun. And you also need to set the environment variable called forkURL, which we will do later. And then match path test curve-b2 exercises curve-b2 price scale.test.sol. Before I copy this, I'm gonna first set my fork URL. So inside my terminal, I have my fork URL stored in a .env file. So let's say cat.env, and then I'll copy this, paste it back inside the code editor. I'll copy this command, and then we'll paste it to execute the test. And to execute the test, make sure that you're under the folder Foundry. Okay, and our test passed. Now take a look at the logs. We see that XP of 0 is approximately 3.8 times 10 to the 24. XP of 1 is 3.75 times 10 to the 24, and XP of 2 is 3.81 times 10 to the 24. What you're seeing here is the amount of USDC normalized to have 18 decimals, so this will be roughly 3.82 million USDC. And then in relative to USDC, we have 3.75 million USDC worth of WBTC and 3.81 million USDC worth of WEF. To swap tokens on Curve-b2 AMM, the user will call the function exchange. For example, here we have the USDC WBTC ETH pool. And let's say that the user wanted to swap ETH to USDC. The user will call the function exchange and then also send ETH to the Curve-b2 pool contract. The Curve-b2 pool contract will calculate the amount of USDC to send back to the user and then transfer this from the pool over to the user. Now, for the contract Curve Crypto Optimized WEF, the user also has an option to swap WEF instead of ETH. For example, instead of swapping ETH for USDC, let's say that the user wanted to swap WEF for USDC. Then in step 1, the user will send WEF over to the pool contract. The pool contract will next convert this WEF back into ETH. To do this, the pool contract will call the function withdraw on the WEF contract. WEF is sent from the pool contract back over to the WEF contract, and in return, the WEF contract will return ETH back to the pool contract. Once the pool contract has ETH, it will calculate the amount of USDC to send back to the user and then transfer this from the pool over to the user. Before we do a code walkthrough for the internal function called exchange, here I'm going to first outline what the code is doing. First, it's going to calculate the A parameter and the gamma parameter. And then it's going to copy the token balances that are stored in a state variable called balances into an array in memory called XP. Next, it's going to update this array XP for token in. And then it's going to update the state variable balance for token in. The next part of the code deals with calculating the transform balances. The first step is to unpack the price scale. Price scale is stored in a single uint256. Once the price scales are unpacked, it's going to calculate the transform normalized balances into this array XP. And here is how this transform normalized balances will be calculated. First, it's going to take the price scale that was unpacked in the previous step, and then multiply by the current value of XP. And then multiply by another value called precisions, which will normalize the token balances to all have 18 decimals. Since price scale also has 18 decimals, here we'll need to cancel out the 10 to the 18 present in the price scale by dividing by 10 to the 18. After doing this calculation, this XP of I will hold the transform balance having 18 decimals. The next step involves calculating the value D if A and gamma are updating. If A and gamma are updating, graphically the Curve-b2 AMM is changing its shape. So we'll need to calculate D given the current inputs and the current parameters, which will determine the shape of the curve B2 AMM at this moment. And this is done by calculating the new value for D and then updating it. The next step is to calculate token out balance. Taking the difference of the new token out balance with the previous token out balance, we can calculate the amount of token out that will go out. Once we know the amount of token out, we can also calculate the swap fee. Update the token out balance, transfer token in, transfer token out, and finally call an internal function called tweak price. If the difference between the current price and the center of liquidity is big enough, Curve B2 will decide to repeg if it has made enough profits. That's what the function tweak price will do. Okay, and that completes the code outline for the function exchange. There are several external functions that a user can call to exchange tokens with the Curve B2 AMM. All of these functions will call an internal function called _exchange. In this video, I'll explain the code inside this function. Let's start with the inputs. We have the sender, and next we have a variable named mValue. Check out for yourself how the function exchange is called, and how the values for mValue is passed. You'll quickly figure out that this mValue refers to message value. Next, we have the index for token in and token out. I will be token in and j will be token out. dx will be the amount of token in, and min dy will be the minimum amount of token out that the user wishes to get back. Next, we have the input use if. If this is true, then either token in or token out is if. So an extra step will be involved converting from if to wef or from wef to if. And then we have the receiver of token out. And then we have two other parameters called callbacker and callbacker sig. The last two inputs are not that important to understand the algorithm for the exchange, so let's figure it out as we go along the code. Okay, so going down, it first checks that I is not equal to j, that the index of token in is not equal to the index of token out. It makes sense. We always want to swap different tokens. Next, it checks that the amount of token in that's going to come in is greater than 0. Okay, moving on. It calculates the current A gamma. Notice that it returns a UN256 array of size 2. The first element will contain the parameter for A, and the second element will contain the parameter for gamma. On the next line, it copies the token balances into an array called XP. Later on, we'll see that this XP will transform into the transform balances. The current token balances will be normalized to all have 18 decimals, and then multiplied by the price scales. Next, it creates a UN256 array of size 3 called precisions. What it's going to do is unpack the packed precisions. Precision is packed into a single UN256 state variable. And here it's unpacking into an array of type UN256 of size 3. This precisions is multiplied by token balances to normalize all of the token balances to have 18 decimals. And then it initializes a local variable called dy. Eventually, this will be the amount of token that will go out. Okay, and on to the next line. Copies the current token balances. Y will be XP of J, and X0, the current token in balance, will be XP of I. Since DX is coming in, it's going to update this XP of I to be the current token balance plus DX. And then update the state variable that holds the current token balance for token in. Next, it copies the state variable price scale packed into memory called packed price scale. And then it unpacks this price scale. Notice that this array called price scale has size n coins minus 1. If there are 3 tokens in the pool, then n coins will be 3. 3 minus 1 will be 2. For a pool with 3 tokens, the reason why this array is of size 2 is because we don't need to store the price scale for the first token. The price scale of the first token will always be equal to 1. Therefore, we only need to store the price scale of the other 2 tokens. And then the next part of the code will calculate the transform balances. What it's going to do is take the token balance, multiply by the price scale, multiply by the precision, and then divide by the precisions. Basically, it's calculating the transform balances, but we need to be careful of the precisions. When we multiply token balance by the precisions, it's going to have 18 decimals. Price scale also has 18 decimals. So at this point, we multiplied 18 decimals by 18 decimals, so we have 36 decimals. To cancel out one of the 18 decimals, we divide by precisions, which is equal to 10 to the 18. Okay, so let's take a look at the for loop. Since the price scale of token 0 is equal to 1, we don't actually need to execute this code. We can simply normalize the token balance to have 18 decimals. And that is what you're seeing over here. Multiply the token balance of token 0 by precisions so that it will have 18 decimals. For token 1 and beyond, we need to multiply by the price scale, multiply by precisions, and then divide by precisions of 10 to the 18. And that is what you're seeing over here. On the next line, it copies the precision for token N, and then it gets the future A gamma time. This is a timestamp that represents when A and gamma will stop updating. If this update is in the future, which you can see over here, if t is greater than block that timestamp, then what it's going to do over here is recalculate the value for d. Okay, moving on. Next, it gets the value for d, and it also copies precisions for token out. Okay, and here's the part that actually calculates the amount of token that will go out. On the first line, it calls a function called math.getY. This will calculate the new token out balance given these inputs. Now, one thing to note here is that this XP represents the transform balances. So the next line, calculating the amount of token out, dy, is equal to xp of j minus y out of 0. These are all calculations done with the transform balances. Since the transform balance of token I increased, the transform balance of token j must decrease. Taking the difference of the previous token j balance with the new token j balance, we get the amount of transform token j that must go out. This is named dy. And then we update the transform token balance for token j, minus 1 from the transform balance of token that's going out to account for rounding errors. And then next it converts the transform token out back into actual token amounts. This is what you're seeing over here. If the index for token out is greater than 0, then we'll need to undo the precisions and the price scale. In the beginning, we also normalized all of the token balances to have 18 decimals. So we'll need to undo that process as well, so that's what you're seeing over here. Okay, and next it calculates the fee. Here it's calculating a dynamic fee by calling an internal function called fee. Minus the fee from the amount of token that will go out, make sure that dy is greater than min dy, and then updates the state variable for the token out balances. And then updates the in-memory token balance, transfers the token in, and for transferring token in, it passes the address for a callbacker and callback sig. You can check for yourself that when this internal function is called, it calls into the address called callbacker, specified by the address over here. Okay, and then it transfers the token out. And next, it calls another internal function called tweak prices. What this is doing over here is it's going to repeg the price if the difference in price from the exponential moving average is big enough. And that completes the code walkthrough for the function exchange. In Curve AMM, fee is calculated dynamically based on the token balances. Here inside the function named _exchange, it's calculating the dynamic fee by calling an internal function called _fee. So in this video, I'll explain the code for this function, and in the next video, I'll show you a graphical representation of what's going on. The first thing it does is unpack a state variable called packed fee parameters. This is a state variable that packs the fee parameters. The fee parameters are an array of size 3 which contain mid fee, alt fee, and fee gamma. Mid fee, we'll see later that this is equal to the minimum fee multiplier. Alt fee will be the maximum fee multiplier. And the last parameter of fee params is called fee gamma. This parameter determines how quick mid fee will increase to alt fee. Next, it calls a math library and calls a function called reduction coefficient, passing in the token balances, xp, and the fee parameters of 2. Fee parameters of 2 is fee gamma. And then it returns a variable called f. This will be the fee multiplier to be applied to the next part of the equation, which is over here. We'll come back to this later. Let me first discuss what's going on inside the function reduction coefficient. This value that is returned called f is calculated by taking fee gamma and then dividing by fee gamma plus 1 minus k. And k will be equal to the product of all the token balances, x0 all the way up to x to the n minus 1, assuming that there are n coins, and then dividing this by the sum of all the token balances, divide by n, and then raise to the power of n. What this is doing over here is that the numerator, the product of all token balances, when we take the nth root, then this will be the geometric mean. And when we take the nth root of this term, the denominator, this will be the arithmetic mean. Add all the token balances, divide by n. So basically, this is taking the geometric mean, dividing by the arithmetic mean, and then raising it to the nth power. And what you need to know from this is that k will be a number between 0 and 1. If you're curious why this is true, you can prove for yourself that the geometric mean of n numbers are less than or equal to the arithmetic mean of n numbers, given that all of the numbers are greater than or equal to 0. Okay, once we know that this k is between 0 and 1, we can also put a lower bound and an upper bound for f. F will be smallest when the denominator is the biggest. The denominator is the biggest when k is equal to 0. And when k is equal to 0, we get that f will be equal to phi gamma divided by phi gamma plus 1. And likewise, f will be the largest when the denominator is the smallest. The denominator is the smallest when this part of the equation is the smallest. And this part of the equation is the smallest when k is equal to 1. When k is equal to 1, 1 minus 1 will be 0. So we get that f will be equal to phi gamma divided by phi gamma. So the upper bound of f will be equal to 1. Before we move on, let's take a quick look at the function reduction coefficient. This function is inside a contract called Curve Cryptoswap optimized. First, you can see that it calculates the sum of 3 tokens. The next part of the code deals with calculating k. Again, k will be equal to the product of all the token balances divided by the arithmetic mean raised to the power of n. That is what you're seeing over here. And lastly, it calculates this part of the equation, phi gamma divided by phi gamma plus 1 minus k, which is what you see over here. You'll also notice that over here it's getting multiplied by 10 to the 18, and then over here it's doing 10 to the 18 minus k. This is because all of the numbers are scaled up by 10 to the 18. So you can think about it as 10 to the 18 being equal to 1. Okay, going back to our main function. So once it calculates f, the last part is to calculate the phi multiplier. The phi multiplier will be a weighted average between the mid phi and the out phi. What you're going to see over here is that it's going to multiply mid phi by f plus out phi times 1 minus f. What you'll see is that when f is equal to 1, this part will be equal to 0, and multiplying 0 by out phi, this part will also be equal to 0. So this function will return mid phi. Now this f is bounded below by phi gamma divided by phi gamma plus 1, which is greater than 0, assuming that phi gamma is greater than 0. But for simplicity, let's say that f is equal to 0. Then what will happen to this equation? Well, the first part is going to be multiplied by 0, so we're left with this part of the equation. Since f is equal to 0, we'll get out phi times 1 minus 0, which is equal to out phi. So what we saw so far is that when f is equal to 1, this part of the code will return mid phi, and when f is equal to 0, this part of the code will return out phi. Okay, but when is f equal to 1, and when is f close to 0? When the pools are balanced, you'll see that k will be equal to 1. And when k is equal to 1, f will be equal to 1, so it returns mid phi. Okay, and when the pool is extremely imbalanced, so k will be close to 0, and when k is close to 0, f will be close to phi gamma divided by phi gamma plus 1. If phi gamma is also a small number that is close to 0, then we can say that f will be close to 0, so the phi that will be returned from here will be close to out phi. So basically what we learned so far is that when the pool is balanced, it will charge a mid phi, which is the minimum fee, and when the pool is extremely imbalanced, then it will charge out phi, which is the maximum fee. Okay, and that completes the code walkthrough for the function phi. In this video, I'll show you graphically how the dynamic phi changes as we change the parameters for mid phi, out phi, and phi gamma. So let's first start by defining the parameters. Let's say f of mid, make this equal to 0.03. So this will be 3%. And f out, this will be the maximum fee. Let's make this equal to 50%. Okay, and then we have the last parameter, phi gamma, f of gamma. Let's make this equal to, let's say 0.1 to start with. Next, I'm going to recreate the equation for the reduction coefficient. I'll name this R of k. Recall from the code that k is the product of all the token balances, divided by the arithmetic mean of the token balances, and then taken to the nth power. So if you want it to be precise, instead of passing in k, we need to pass in all of the token balances. But we also know that k will range from 0 to 1. So that is what we'll do over here. What you're going to see on the graph is that on the horizontal axis, we'll map the value for k from 0 to 1, and then on the vertical axis, we'll map the phi multiplier. So rk is equal to phi gamma divided by phi gamma plus 1 minus k. This function calculates the reduction coefficient. Okay, moving on. let's recreate the function that calculates the fee multiplier. I'll call this f of k equals to. We saw that the fee multiplier is the weighted average of mid fee and out fee. So say f mid times the reduction coefficient r of k, and then plus out fee f of out times 1 minus the reduction coefficient r of k. Okay, and this is the graph that we get for the fee multiplier. Let's zoom in. Next, I want to see where mid fee and out fee are. So let's say y is equal to f of mid, and also y is equal to f of out. The maximum fee multiplier will be 0.5, and the minimum fee multiplier will be 0.3. And the fee multiplier, f of k, will change dynamically as k changes. K will range from 0 to 1, so we don't need to consider this part of the graph. So what I'm going to do is show you f of k for k ranging from minus infinity to infinity. This is what you see with the dotted lines. And in pink, I'm also going to show you f of k for k between 0 and 1. When k is equal to 0, this means that the pool is extremely imbalanced. Then the fee that will be charged is close to the maximum fee. And when the pool is perfectly balanced, k will be equal to 1, so the fee that will be charged will be the minimum fee. So that's what's going on with this function, the fee multiplier function. Next, let's see what happens to this graph as we change the parameter for fee gamma. So when we increase the fee gamma, you can see the fee multiplier becomes flat like a slanted line. What happens if we decrease this parameter? So as we decrease the fee gamma parameter, you can see that the pink graph bends more quickly. So you can see from here that when fee gamma is small, the fee multiplier will quickly increase from mid fee to out fee. However, when fee gamma is large, then the fee gamma is slow to increase from mid fee to out fee. Here's the first exercise for swapping with Curve B2 AMM. The exercise is located under test, Curve B2 exercises, Curve B2 swap.test.so. Okay, let's take a look at the first exercise. For this exercise, we're going to be using the Curve B2 pool that has USDC, WBTC, and WEF. So for the first exercise, call get dy to calculate the amount of USDC for swapping one WEF to USDC. And write your code here. Okay, let's go over the solution. So we need to call the function get dy on the pool contract. The interface is defined over here. So let's take a look at this interface to see how we will call the function get dy. The interface is located under source, interfaces, curve, and then I try crypto. Okay, so here is the interface. And to call the function get dy, you'll need to call this function. For the input, it's going to take in the index of the coins. I will be the index of the token to put in, and j will be the index of the token that will go out. And dx is the amount of token to put in. Okay, so going back to our exercise, here we'll need to call pool.getDy. For this exercise, we're going to calculate the amount of swap for one WEF to USDC. Okay, going back over here, WEF will be the third token in this pool. So the index of this token will be 2. USDC will be the first token in this pool. So the index will be 0. We're swapping from token 2 to token 0, which is WEF to USDC. The amount of WEF that we're going to put in is 1 WEF. WEF has 18 decimals, so 1 WEF will be 10 to the 18, or we can write this as 1e18. Okay, and that completes the exercise. Note here that we're not actually swapping the tokens. Here we're querying for the estimate of how much token that we will get if we were to put in this much amount of WEF. Okay, let's try executing the exercise. To execute this exercise, I'm gonna execute this command. What's important here is that you'll need to set the environment variable for fork URL, and also to make sure that we only execute the test for get dy, we'll put in an extra parameter saying match test get dy. And also it's important that you specify the EVM version to be Cancun. Next, we'll execute this exercise by copying this command and then pasting it here. Okay, and our test passed. Let's take a look at what the console log printed out. dy is equal to 3.07 times 10 to the 9. USDC has 6 decimals, So this will be about 3,070 USDC. If we were to put in one WEF, the estimate amount of USDC that we will get is 3,070 USDC. The second exercise for swap is to swap one WEF to USDC. Now you might be wondering, where did we get this one WEF from? Inside the setup, you can see this contract is given one WEF, and the next line is also important. It approves the pool to pull the WEF from this contract. So these two setup will make sure that the swap will be successful if you write the code correctly. So the exercise is to call exchange on the pool contract to swap one WEF to USDC. Let's go over the solution. First of all, how do we call the function exchange on the pool contract? To answer this question, let's take a look at the interface. The interface for the iTryCrypto is located under source interfaces iTryCrypto. And then inside here, we see the function exchange. Let's copy this. And then back inside our exercise, let's paste this code. Okay, so this is the function that we will need to call. The contract that we will need to call is pool. So pool.exchange. Now there are several parameters that we need to pass here. To make it easy for us to understand what parameter we're passing, here I'm going to put a curly braces and then also a closing curly braces over here. And then for the first input, we're going to be swapping from WEF to USDC. WEF inside the pool contract is indexed at 2. And then USDC is indexed 0. DX, the amount of WEF that we're going to be putting in. We'll put 1 WEF, so this is 1E18. Min DY, the minimum amount of USDC that we expect to get back. For simplicity, let's put this as 1. And then use ETH. Are we going to be using ETH instead of WEF to exchange for USDC? In this case, we're not. We're using WEF, so this will be false. And then the address of the receiver. Let's set this to this contract. Address this. Okay, so that completes the second exercise. Let's try executing the test. To execute the test, we'll call the function test exchange. So we're going to be executing this command, except the test that we're going to execute is test exchange. Okay, let's try executing this command. I'll copy this, and then inside my terminal, I'll paste it, execute the command. Okay, and our test passed. For swapping one WEF, we got back 3,080 USDC. Traders can swap tokens with the Curve B2 AMM. But how are these tokens put inside this pool contract in the first place? This is what liquidity providers do. Liquidity providers deposit token into the Curve B2 AMM. In return, they'll be able to claim the swap fees that are collected from the traders. Now, as a liquidity provider, you'll be unhappy if these tokens are stuck inside the pool contract forever. So they'll have the option to remove their liquidity whenever they want. Let's look at an example for a USDC WBTC ETH pool. To add liquidity, a user will call the function add liquidity, specifying the amount of USDC, WBTC, and ETH to deposit into the Curve B2 AMM contract. Now, similar to Curve B1, there is no restriction on the amount of tokens that the user can deposit. For example, a user can decide to put in 100 USDC, 0 WBTC, and 0 ETH. Or they can also add equal amounts, 100 USDC, 100 WBTC, and 100 ETH. Once the user adds liquidity, the pool contract will mint liquidity provider shares, and it represents the percentage of liquidity owned by this user. And what is liquidity? Well, liquidity can mean different things with different AMMs. The basic idea of liquidity is you take the token amounts and you take some parameters, do some math, and come up with a number. For example, for a constant product x times y equals L square, the liquidity is calculated by multiplying the token balances and then taking the square root to solve for L. So that's in constant product AMM. In Curve B2, liquidity is calculated by using a more sophisticated math. Now, a user also has an option to add liquidity using WEF. This is similar to swapping with WEF in Curve B2. If they choose to add liquidity and use WEF instead of ETH, then after the WEF is transferred over from the user to the pool contract, the pool contract will call withdrawal on the WEF contract. The WEF contract will take the WEF owned by the pool contract and then transfer ETH back to the pool contract. Here I will briefly outline the code for the function add liquidity. It's going to take in several inputs, but the one that I want to highlight here is amounts. This will be the amount of token to add as liquidity. Now, similar to Curve B1, you can specify any amount of tokens that you want to put in. If the amounts that you add end up changing the price given by the AMM, then you'll be charged the imbalance fee. Inside the function, it first calculates A and gamma. Next, it copies the token balances into an array initialized in memory called XP. And then it will add these amounts from the input to this array XP, and then update the state variable token balances. Next, the in-memory array XP is used to store the transform normalized balances. Token is transferred in, and if A and gamma are currently updating, the function will calculate D before liquidity is added. And then the new D based off of the transform token balances after adding liquidity is calculated. Next, LP shares to mint is calculated. The amount of LP tokens to mint is named D token, and the way it is calculated is take new D divided by old D, multiply by total supply, and then minus the total supply. This ratio here will represent the growth in D. Multiply this by total supply, where total supply is the total supply of LP tokens that are minted so far. And this will represent the new total supply. Taking the difference from the current total supply, this will give us the amount of LP tokens that needs to be minted. Next, it will calculate the imbalance fee. Since there's no restriction on the amount of tokens that can be added as liquidity, you can add tokens in a way so that the ratio of token balances will change. This will result in the pricing of the tokens to change, and hence imbalance fee will be charged. Next, the imbalance fee is deducted from the amount of LP tokens to mint. LP token is minted, the internal function called tweak price is called. And lastly, it calls the internal function claim admin fees. Let's do a code walkthrough for the function add liquidity. As the name says, this is a function that the liquidity providers will call to add tokens into Curve B2's AMM. It takes in 4 inputs. Amounts will be the amount of token to put in. Mint amount will be the minimum LP token that the liquidity provider wishes to get back. Use ETH if instead of sending ref, the liquidity provider is sending ETH. And then the receiver will be the receiver of the LP token. The function is going to return a UN256, which represents the amount of LP token that was minted. Okay, scrolling down. First, it calculates A and gamma. Next, it initializes an array called XP, and it copies the state variable balances, which hold the token balances. Later on, you'll see that this XP will turn into the transform balances. And then we have a variable called amounts_b. This is initialized to be a UN256 array of size and coins. Later on in the code, you'll see that this is equal to XP minus old. XP will be the transform balances after adding liquidity, and XP old is the transform balances before adding liquidity. So taking the difference, we'll get the transform amount of tokens that came in. And then it initializes some few more variables, but we'll skip the explanation for now and we'll figure it out as we go along. So first it checks that some amount of token was added as liquidity. Amounts will specify the amount of tokens that the user wishes to put into this pool. Here it checks that the sum of the tokens that the user is going to put in is greater than 0. Okay, next it unpacks some of the packed state variables, precisions, packed price scale, and price scale. And then next it updates the state variable balances. Balances of I will be equal to BAL, where BAL is equal to XP of I plus amount of I. Remember that at the beginning of the function, XP of I was initialized to be self.balances, the copy of token balances, and amount of I will hold the amount of token that the user is going to put in. So XP of I plus amount of I will be the new token balance. And then the next part of the code will calculate the transform balances, XP and XP old. XP will be the new transform balances after adding liquidity. XP old will be the old transform balances, so this will be before adding liquidity. Okay, and then going down further, next it transfers from tokens into the pool. So it transfers the tokens into the pool. And then it sets amounts P to be equal to XP of I minus XP of old. So this will represent the transformed amount of tokens that came in. Okay, and then next part of the code, calculate LP tokens to mint. First it checks that if future A gamma time is greater than the current timestamp, so this means that A and gamma are going through an update, then it calculates the number D with the current A gamma parameters and the old transform balances. Otherwise, if A and gamma are not going through an update, then it just uses the old value for D, which is stored in a state variable called self.d. And then the next part of the code will calculate the new D. The new D will again use the same A and gamma parameters, but however XP here will represent the new transform balances. Okay, and this part of the code will calculate the amount of LP tokens to mint. If old D is greater than 0, then this assumes that liquidity was previously added to this pool. In this case, the amount of LP tokens to mint is calculated by taking the current token supply, the current LP token supply, and then multiplying it by the ratio of change in the value D divided by old D. This division will give the ratio of how much D increased compared to old D. And then minusing this value from the current token supply will give us the change and the LP token supply. Otherwise, if old D is equal to 0, then this is assumed to be the first time that liquidity is added. In this case, the amount of LP tokens to mint is calculated by calculating the pool value, where the pool value is equal to D divided by N times the price scale of token 0 times D divided by N times the price scale of token 1, and so on, all the way up to the last token, and then taking the nth root. Next, it checks that the amount of LP tokens to mint is greater than 0, and if old D is greater than 0, then it's going to calculate a fee on deposit called D token fee. We'll come back to how this fee is calculated, and then it's going to minus this from the amount of LP tokens to mint, and then actually mint the tokens. And after it mints LP tokens, it will call an internal function called tweak price. Otherwise, if old liquidity is equal to 0, then it will set the state variable D to the new D, and virtual price XCP profit, XCP profit A will all be set to be 1. And then it will call the internal function mint to mint LP tokens. Log the event, and then call an internal function called claim admin fees. Next, let's take a look at this internal function called calc token fee. This function is going to calculate the percentage of fee to charge. For the input, it's going to take in amounts and XP. The amounts will be the transformed amounts of token that came in, and XP will be the transformed token balances. First, it calculates the fee multiplier, and you can see over here that it calls the internal function called fee. This is the function that is responsible for calculating the fee multiplier dynamically based on XP. And then it's going to multiply by N coins, and then divide by 4 times N coins minus 1. So this fee will turn out to be this equation over here. This part of the equation, N divided by 4 times N minus 1, seems to come out of nowhere. However, if you learn Curve B1, then you'll see that in Curve B1, you'll see the same code. Basically, this number is derived from making sure that imbalance fee for adding liquidity and then removing liquidity is the same as the swap fees. For more information, I'll put a link in the GitHub repo. Okay, and then moving on, next it calculates the sum of amounts of tokens that came in. Next, it will calculate the average of S divided by N coins. And then the next part of the code over here, it's going to sum up the difference between the average and the actual amount of tokens that came in. So what's going on over here is that it's summing amounts of buy, comparing this with the average of amounts, and then summing all of this. And inside the code over here, what it's doing is taking this sum, multiplying by fee, and then dividing by the sum of amounts plus what's called noise fee. Notice that when the transformed amounts are all equal to each other, then the average will be equal to this number as well. So taking the difference of amounts of buy with the average of amounts will always be equal to 0. This part will be equal to 0, multiplying 0 by another number will be 0. And the resulting fee will be equal to 0 plus some noise fee. Okay, that ends the code walkthrough for the function calc token fee. Here is the exercise to add liquidity to a Curve B2 pool. The pool that we're going to be working with for this exercise is the USDC WBTC WEF pool. For the setup, this contract is given 1000 USDC. And the next line is also important. It approves the pool contract to spend USDC from this contract. These two setups will allow us to add liquidity from this contract. Okay, so the first exercise is to call add liquidity. Add 1000 USDC as liquidity to the pool contract. Write your code inside here. Let's go over the solution. Let's first see how we can call the function add liquidity. What parameters do we need to pass? Okay, here I have the interface for the iTryCrypto open already. And if you're looking for this, it's on the source interfaces curve iTryCrypto. The function that we'll need to call is add liquidity. Let's copy this and then paste it here. The contract that we'll need to call is pool, and then the function is add liquidity. It's going to return the amount of LP shares that was minted, but we will not need this for this exercise. Okay, and these are the parameters that we'll need to prepare. Let's start with an array of size 3 that specifies the amount of each token that we're going to put in. So let's create an array in memory, uint 256 of size 3, memory, let's call this amounts, is equal to, and then let's say uint 256, 1000 USDC. So this will be 1000 is 1000, and then USDC has 6 decimals. Multiply this by 1e6. And the rest of the numbers can be 0. Uint 256 0, uint 256 0. So here we're specifying that we're going to add liquidity, and the amount of tokens that we're going to add is 1000 USDC, 0 WBTC, and 0 WEF. So the first parameter is prepared. Here I'm going to use the curly braces so that I can specify which input corresponds to the value that we're passing in. So amounts will be the amounts array that we just prepared. Min LP, minimum amount of LP shares that we expect to get back for adding this much as liquidity. For simplicity, we'll just put 1. And use ETH. Are we going to use ETH to add liquidity? Since we're adding USDC, we're not going to be adding any WEF or ETH. Set this to false. Receiver, the receiver of the LP shares. Adjust this. This completes the exercise. Let's try executing this test. So the command that we'll paste is this over here. Forge test, specify the EVM version as Cancun, specify the 4Q arrow, and the test is located under test, curve B2 exercises, curve B2 add liquidity. Copy this command inside my terminal, I'll paste it, execute, and our test passes. A liquidity provider can remove liquidity from a curve B2 AMM by calling the function remove liquidity. To remove liquidity, the user will call remove liquidity, specifying the amount of LP shares that they want to return back to the pool. This LP shares is a ERC20 token, and the pool contract will burn this LP shares. Calculate the amount of USDC, WBTC, and ETH to send back to the user, and then transfer it to the user. The user also has an option to withdraw in WEF instead of ETH. If they choose to do so, after this LP share is sent back to the pool contract, the pool contract will convert the ETH that was supposed to be sent back to the user into WEF. This is done by calling the function deposit on the WEF contract. The WEF contract will receive this ETH and then turn it into WEF. And instead of ETH, WEF will be sent back to the user. Before I do a code walkthrough of the function remove liquidity, here I will outline what's going inside the code. Inside the function, it's going to first call an internal function called claim admin fees. And then it's going to burn the amount of LP shares that was specified by the user, calculate the amount of tokens that will be sent back to the liquidity provider, update the internal token balances. The number D that is used for the curve B2 AMM's equation is stored in a state variable called D. So this will be decreased, and then the tokens will be transferred out. The function remove liquidity is called by the liquidity provider to withdraw their tokens in exchange for burning the LP shares. For the inputs, it's going to take in amount. This will be the amount of LP shares that the liquidity provider is going to burn. And then the next input is called min amounts, the minimum amount of tokens in the pool that the liquidity provider wishes to get back. Okay, let's look inside the function body. First, it initializes some variables, amount, balances, which will be the state variable, self.balances. This state variable will hold the amount of tokens in the pool. And then next, we have an array called dbalances. Let's scroll down a little bit further to see how this variable is used. Okay, next we have if claim admin fees, then call the function claim admin fees. And then it's going to cache the total supply, the state variable total supply, into a local variable, and then call the function burn from to burn the LP shares of message sender. And then next it calculates the amount of tokens that will go out. This is called dbalances. If the amount of LP token to burn is equal to the total supply, then the amount of token that will go out is the current internal token balances. Balance is a byte. And then afterwards, it will set the internal token balances all to 0. Otherwise, if the amount is less than the total supply, then it first minuses 1 from amount. I think this is done so that when there's some kind of calculation, the math will round down in favor of the pool contract. Okay, next we have a for loop. The for loop will range from I equals to 0 to I less than n coins. And for each iteration, it will calculate the amount of tokens that will go out. D balance is a buy is equal to the current balance, the current internal token balance is a buy. Multiply this by the LP shares that the liquidity provider is going to burn, divide by the total LP shares. Next, it checks that this D balances, the actual amount of tokens that will go out is greater than the min amounts that was specified by the caller. update the token balances, and then also update the balances array. Here it's updating to the actual amount of tokens that will go out. So I'm guessing that this balances will now be used for something else. Okay, so let's scroll down to see the rest of the code. It will cache D into a local variable, and then it will calculate the new D. The new value for the state variable D is equal to the current value for D minus D multiplied by the amount of LP tokens to burn divided by the total LP tokens. What's going on here is that let's say that the new value for D is D1 and the current value for D is D0. Then the ratio D1 divided by D0 will be equal to the new LP supply. This is given by total supply minus the amount of LP shares to burn divided by the current LP supply. And what this equation is saying is that the decrease in D from D0 to D1 must be in the same ratio as the decrease in the total supply of LP tokens from total supply to total supply minus amount. And solving for D1, we multiply both sides of the equation by D0, the current value of D. And we would get D1 is equal to D0 times this ratio. And if you simplify this, you'll get this equation. Okay, and then moving on, it transfers the tokens out, logs the event, remove liquidity, and then returns the actual amount of tokens that was transferred over to the liquidity provider. The first exercise to remove liquidity from Curve B2 is to call the function test remove liquidity. Let's take a look at the setup. The pool contract that we're dealing with is the USDC, WBTC, and the WEF pool. Inside the setup, this contract mints 1000 USDC to itself and then approves the pool contract to spend this USDC. Since the exercise deals with removing liquidity, inside the setup, we also add liquidity to mint some LP shares. And here you can see that it adds USDC as liquidity. So after this code executes, this contract has some LP tokens that it can use to withdraw liquidity. So for the first exercise, I want you to call the function remove liquidity on the pool contract to remove all of the liquidity that is possible by this contract. To do this, you'll need to first figure out the amount of LP shares that this contract has. Since the TryCrypto is a ERC20 token, you can simply call pool.balanceOf, querying the balance of this contract. Once you have the LP balance, call remove liquidity to remove all of the liquidity that this contract can. Let's go over the solution. To call the function remove liquidity, what parameters do we need to pass? Well, let's take a look at the interface iTryCrypto. The interface, if you're looking for this interface, is located at source interfaces curve iTryCrypto. The function that we'll need to call is remove liquidity. Let's copy this, and then back inside our exercise, I'll paste the function over here. Okay, so this is the function that we'll need to call, and these are the parameters that we'll need to pass. The contract that we'll need to call is pool, and then the function is remove liquidity. Here again, I'm going to use the curly braces so that it makes it easier to understand what inputs we're passing in. For the output, it's going to return the amount of tokens that was sent back to this contract. Here, we're not going to need this. Okay, so let's prepare the inputs. We first need to specify the amount of LP shares that we're burning. So let's first get the amount of LP shares that this contract owns. uint 256, let's call this LP val, is equal to pool dot, and how do we get the LP shares owned by this contract? Since the pool is a ERC20, we can simply call balance of, and then say address this. Okay, once we have this LP balance, we're going to be burning all of this LP shares. So for the amount of LP to burn, let's say LP val, all of the balance of this contract. Next, min amounts. You'll need to prepare a uint array of size 3. Let's say uint 256, size 3, memory. Let's call this min amounts. And then, since we want all 3 tokens, and to keep it simple, let's just put 1 for all of them. uint 256, 1, and the same for the other 2 tokens. So min amounts will be the min amounts array that we just prepared. Use if. Do we want if back? We want WEF back, so this will be false. Receiver will be this contract, the address that's going to receive the tokens. And then claim admin fees. Do we need to claim admin fees? I'm not sure. I'll just put it as false. Before we execute the test, I'm going to remove this comma, which is going to cause a compilation error. So the test that we're going to be executing is called test remove liquidity. Here I want to execute only the test called test remove liquidity. However, inside this contract, there are 2 tests, test remove liquidity and test remove liquidity one coin. To make sure that we're going to execute the exercise test remove liquidity, here I'll have to type test remove liquidity. Then we'll need to do a special regular expression //b. This will make sure that the only test that is matched is test remove liquidity and not test remove liquidity one coin. Okay, let's execute this exercise. I'll copy this command and then paste it here and then execute the exercise. And our test passed. And these are the amounts of tokens that we get back for removing liquidity. When we added liquidity, we added about 1000 USDC. When we remove liquidity, we get back about 330 USDC, this much amount of WBTC, and about 0.1 WEF. The liquidity provider will call the function remove liquidity one coin if they wanted to remove their liquidity all in a single token. For example, if they were to call the function remove liquidity, then they will receive all three tokens, USDC, WBTC, and ETH. However, by calling the function remove liquidity one coin and specifying which token they want, they'll be able to receive their liquidity in a single token. So, for example, let's say that we have the USDC, WBTC, ETH pool, and the liquidity provider wants to remove all of his liquidity and ETH. They'll call the function remove liquidity one coin and then returning the LP shares that they own. The pool contract will burn this LP shares, calculate the amount of liquidity that needs to be sent back to the user, and since the user specified that they wanted to receive their liquidity in ETH, the pool contract will calculate the amount of ETH to be sent back to the user, and then send the ETH from the pool contract to the user. The user also has the option to receive WEF instead of ETH. If the user specified that they wanted to receive their liquidity in WEF, then after the LP is sent back to the pool contract, and the pool contract calculates the amount of ETH to send to the user, instead of sending this ETH to the user, this ETH will be deposited into the WEF contract. The WEF contract will convert this ETH into WEF, and the pool contract will send the WEF back to the user. Inside the function remove liquidity one coin, it will first calculate A and gamma. Next, it will call the internal function claim admin fees. And then it's going to call another internal function to calculate dy. This will be the amount of token that will come out, and the new value for D, and then the fee that was charged for removing liquidity only in one coin. Update the token out balance, burn the LP shares, transfer token out, then call internal function called tweak price. Let's do a code walkthrough for the function remove liquidity one coin. This function will allow the liquidity provider to specify which token they want their liquidity withdrawn in. For the input, it's going to take in token amount. This will be the amount of LP shares that the liquidity provider wishes to burn. And I will be the index of the coin that they want to withdraw their liquidity in. Okay, let's look at the function. First, it calculates A and gamma, and then initializes some variables. Next, it calls an internal function called claim admin fees. And then it calls an internal function called calc withdraw one coin to calculate the amount of token that will go out, dy. Checks that this dy is greater than or equal to the minimum amount. This minimum amount was specified by the caller. Update the token balances. Since here only one token is exiting the pool, we only need to update the balance for the token that is going out. And then burn the LP tokens from message sender for the amount token amount, transfer the token out, call the internal function tweak prices, log the events, and then return the amount of token that was transferred out. Inside the function remove liquidity one coin, the way it calculates the amount of token that will be sent back to a liquidity provider is by calling an internal function called calc withdraw one coin. So in this video, I'll explain the parts of the code that are a little bit confusing inside this function. Okay, here's the function calc withdraw one coin. This function will calculate the amount of tokens that the liquidity provider will receive for burning this much amount of LP shares. Here the variable I specifies which token the liquidity provider wants to get. Okay, first it caches the state variable total supply. This will be the total LP supply, and then does some basic checks. Checks that the LP shares that is to be deducted is less than or equal to token supply, and also checks that the index of token I is less than n coins. Initializes some more variables. XX is initialized to be the token balances, and then it unpacks precisions into array, and then it copies this precisions into a variable called XP. Later on in the code, you'll see that this XP will represent something else. And then it initializes a variable called D0. Okay, let's go further down. Immediately we see some code that are a little bit difficult to understand. So let's see what's going on here. The easiest way to understand what's going on here is to try to understand what gets stored inside the array XP for each iteration. Inside the for loop, the iteration will run from k equals to 1 to k less than n coins. And let's see how XP of k is updated. What it's doing here is multiplying XP of k with XX of k and then multiplying by P, where P will be the price scale, which is defined over here. And then it's dividing this whole multiplication by precision. Remember that XP of k was initialized to be the precision and XX was initialized to be the balance. So what's being stored in XP of k is the precision of token k, multiplied by the balance of token k, multiplied by the price scale, and then divide by precisions. So now we understand that XP of k stores the transform balance of token k. Okay, but the for loop runs from k equals 1 to less than n coins. How about for k equals to 0? Well, for k equals to 0, the price scale is 1, so we don't need to perform this calculation. Instead, it just multiplies XP of 0, which stores the precision, by the token balances, which is stored in XX of 0. So after this part of the code is done executing, what we end up with is that XP stores the transform balances. Okay, and then moving on, if update D, so this update D comes from the input. If this is true, then recalculate the value for D, and it is called D0. Otherwise, just use the D from the state variable. Okay, and then moving on, it next copies D from D0. I'm guessing that later on D will be compared with D0 to calculate the amount of token that will go out. Okay, and then scrolling down, first it initializes two variables called XP imprecise, which is a copy of XP. So this will be a copy of the transform balances, and then XP correction, which is XP of I, where I is the index of the token to withdraw, multiplied by n coins, multiplied by token amount, divided by total supply. And how these two variables are being used is over here. Over here, it says that XP imprecise of I. So from the transform balance of token I, which is the token to be withdrawn, minus XP of correction. So this part of the code is a little bit confusing to understand. But the way to understand this is from reading the comment over here. Here it says that XP is adjusted, assuming that XP of 0 is close to or equal to XP of 1, and which is close to or equal to XP of 2. So assuming that all of the XP, all of the transform balances are close to each other, then if we were to do a balanced withdrawal, then from XP of 0, the amount that we will withdraw is XP of 0 times token amount divided by total supply. Deduct XP of 0 in proportion to the amount of LP shares that are to be burnt. And the same goes for XP of 1. Deduct from XP of 1, the amount to deduct is given by the current transform balance, XP of 1, multiplied by the token ratios, token amount divided by total supply. And the same goes for XP of 2. These are the amounts that are to be deducted if we were to do a balanced withdrawal. And you can see this code inside the function remove liquidity. Okay, but how about imbalanced withdrawal? Well, assuming that all of the transform token balances are equal to each other, then this value will be close to XP of I. This is the token to be withdrawn. Since there are n coins, we multiply this by n. And then the token ratios are the same. Basically, what's going on here is assuming that all of the transform balances are equal to each other, when we sum up these values, the sum of these values should be close to this calculation. Okay, so that's what XP of correction represents. XP of I multiplied by n coins multiplied by the token ratios. And then next, it gets the fee multiplier, the max fee multiplier, which is stored in packed fee params. Okay, and then moving on, remember XP of correction now represents XP of I multiplied by n, and then multiplied by the token ratios, the LP token ratios. If we were to withdraw approximately this much amount of token from XP of I, then we need to make sure that there's no underflow. So we first check that XP correction, which is this amount, is less than XP imprecise of I, which currently stores the transform balances XP of I. Okay, so if XP of I is greater than this amount, then we safely deduct it. And now, using this XP imprecise, which represents the transform token balances, after deducting this much amount from XP of I, then we calculate the fee multiplier. Now the fee multiplier will range from min fee multiplier and max fee multiplier, which are all specified by this packed fee params. So that is how the fee multiplier is calculated. Okay, but how about the case if XP correction is greater than or equal to this number? Well, in that case, the fee multiplier already is set to the max fee multiplier, so we don't need to handle that case. So that's how the most confusing part of the code, this part of the code, works. Okay, and then moving on. Next, it calculates the change in D. The change in D will be the current D multiplied by the LP shares to burn, divided by the total LP supply, token supply. Here we're saying that we're going to decrease the current value of D by the ratio token amount divided by total supply. And from this DD, a fee is calculated. The fee is calculated by multiplying the fee multiplier by the change in D, and then dividing by 2 times 10 to the 10. I'm not entirely sure what this number represents, but I'm guessing that this will represent some kind of fraction, so that it is saying some fraction, some percentage of fee multiplied by DD, and then plus 1 to round up. Okay, next it calculates a variable called approximate fee. Here we won't worry too much about this, since this is only used inside the events. The event will emit this value, so it's not used in the rest of the calculation. Okay, moving on. From the current value of D, deduct DD, but also keep D fee. And then the next part of the code involves calculation of the new value for Y, which is the token balance of XP buy, after the value D has decreased by DD plus D fee. Okay, so from this new token balance, we calculate the amount of token that will go out, and then update XP buy to be this new token balance. And then that completes the code walkthrough for the function calc withdraw 1 coin. For the second exercise in removing liquidity, I want you to call the function remove liquidity 1 coin. For the setup, this contract has added 1000 USDC as liquidity. And here I want you to return all of the LP shares owned by this contract back to the pool contract, and then withdraw liquidity in a single token, USDC. Let's go over the solution. Let's see how we will call the function remove liquidity 1 coin. Inside the interface I try crypto, we'll need to call the function remove liquidity 1 coin. I'll copy this function, and then back inside our exercise, and paste it here. The contract that we'll be calling is pool. Call the function remove liquidity 1 coin. And then we don't need the outputs. The output is the amount of token that was returned from the pool contract. Okay, let's prepare the inputs. LP is the amount of LP shares to burn. We're going to be returning all of the LP shares owned by this contract. So let's first get the amount of LP shares that this contract owns. Uint 256, let's call this LP val equals pool.balance of address this. Okay, once we have the LP val, we can specify it here. LP is LP val. Next is I. This will be the index of the token that we wish to get back. For this exercise, we want USDC back. Index of USDC is 0. Okay, moving on, min amount. Minimum amount of USDC that we expect to get back. Let's just put it as 1. Use ETH. Do we want ETH back? We want USDC back, so we don't want ETH back. False. Address of the receiver. The receiver of USDC will be this contract. Address this. Okay, that completes this exercise. Let's execute this test. The name of the test is called test remove liquidity 1 coin. Going back up, here we'll need to match the test remove liquidity 1 coin. Copy this command, and then inside the terminal, paste it, execute, and the test passes. Notice here that inside the logs, the amount of USDC that we got back is approximately 9.99 times 10 to the 8. This is about 999 USDC. And the amount of WBTC that we got back is 0, and the amount of WEF we got back is 0. This is because when we call the function remove liquidity 1 coin, we specify that the token that we want the liquidity back in is only in USDC. The Curve CPAMM has an internal price oracle that stores the exponential moving average of the prices. To understand how this exponential moving average of the prices is calculated and also stored in the smart contract, I first want to explain the math behind the exponential moving average. And the math involves 2 parts: understanding exponential moving average for regular intervals, and then we'll move on to understanding the exponential moving average for irregular intervals. Here, regular interval means that the price is updated in a regular interval, for example, every 1 second. An irregular interval will mean that there is no fixed duration where the price is updated. And this is the nature of the blockchain. There's no guarantee on when the updates will happen. So let's start by looking at the math for exponential moving average or regular intervals. Let's say that we have some price of the token. On the horizontal axis, we'll graph the time, and on the vertical axis, we'll plot the price of the token. We'll denote P of t to be equal to the price at time t. The graph of the exponential moving average of the price will look like a smoothed out version of the price graph. Since the exponential moving average is taking some kind of average of the prices, the price given by the exponential moving average will lag behind the actual price. To calculate the exponential moving average, we first initialize m of 0 to be equal to p of 0. The exponential moving average at time 0 is initialized to be the price at time 0. And for all values t greater than 0, the exponential moving average will be defined as a weighted average of the current price, p of t, and the previous exponential moving average, m of t minus 1. The weight is defined by a constant between 0 and 1. For example, we can pick 0.5. And then we multiply the current price p of t by a, and multiply the previous exponential moving average with 1 minus a. What's going on here is that it's taking the weighted average of the past and the present prices. So this is how the algorithm works. Let's take a look at an example, and it will also explain why this is called the exponential moving average. Let's start by calculating the exponential moving average at time t equals to 100. By definition, this will be equal to the current price, let's say p at time t equals 100. To this, we'll need to apply a weight and then add the previous exponential moving average, m of 99. The exponential moving average at time t equals 99. The weight is defined to be a constant a. So to the current price, we multiply this by a, and to the previous exponential moving average, we multiply by 1 minus a. Okay, but what is m of 99? Well, m of 99 by definition is equal to the constant a multiplied by the price at time t equals to 99, plus 1 minus a multiplied by the previous exponential moving average. Exponential moving average at t equals 98. Okay, so we have m98 over here. But what is m98 equal to? Well, again, we unpack the definition. We multiply the price at time t equals 98, multiply this by a. And then to this, we add 1 minus a multiplied by the previous exponential moving average, m of 97. And this continues until we reach m of 0. To see where the term exponential comes from, we'll expand m of 100. By definition, this is what m of 100 is equal to. We also know what m of 99 is equal to. So let's unpack m of 99. Okay, here is m of 99. Next, let's unpack this term. This term is multiplied by 1 minus a. So we get 1 minus a multiplied by a times p99, which you see over here. And then we multiply 1 minus a by 1 minus a times m98. Since we're multiplying 1 minus a by itself, we have 1 minus a to the square times m98. And when we unpack m98, by definition, m98 is equal to this term. We can do this again to unpack m97. So copy this and then paste it here. Okay, so let's unpack m97. The first term, a times p of 98, is multiplied by 1 minus a raised to the power of 2. And then the next term is also multiplied by 1 minus a raised to the power of 2. Here we have 1 minus a raised to the power of 2 minus 1 minus a. So this will turn out to be 1 minus a raised to the power of 3. And then we can remove this. Okay, so we have m97 left. Are you starting to see a pattern here? For every term, we have 1 minus a raised to some power, and this power increases by 1. Here we have 1 minus a raised to the power of 0. Here we have 1 minus a raised to the power of 1. Here we have 1 minus a raised to the power of 2. And here we have 1 minus a raised to the power of 3. You can check for yourself that when you expand all of the terms up to m0, what you'll notice is that each term will have 1 minus a multiplied by a, and then multiplied by the price. And 1 minus a will be raised to some power. As we move to the right, the power that is being multiplied by 1 minus a will increase. Here we have a 2, here we have a 3, and so on. And at the end, we'll have 1 minus a raised to the power of 100. And this is where the term exponential comes from. The prices in the past are multiplied by 1 minus a raised to some power. What's happening here is that the prices in the past experience exponential decay. So when we take the exponential moving average, the prices that contribute most to the average will be the prices that are close to the latest price. Here I'll show you an example of simulating the exponential moving average for regular intervals using Python. For you to go through this example, you'll need to have Jupyter Labs installed and the extension Jupyter. The file that we'll work with is located under Notebook, Curve B2 EMA. First, we'll need to start the Jupyter server. So inside my terminal, I'll type Jupyter Lab. Inside the server logs, you'll see a comment saying that to access the server, copy this URL. And then back inside our code editor, we'll connect this code editor to the Jupyter server by clicking on Select Kernel, click on Select Another Kernel, existing Jupyter server, and then paste the URL, and then click on Connect. We also need to select which Python we're going to be using, so I'll click the Python for Jupyter session. Okay, we're now connected. Next, we're going to install some Python library that we're going to need for this example. The library that we're going to need are called NumPy and Matplotlib. Once you install NumPy and Matplotlib, we'll next write some Python code. And to do this, I'll click on this plus code. And inside here, we'll start writing our Python code. I'll first import the libraries that we just installed. Import NumPy as np and import matplotlib.pyplot as plt. And then next, I'll define a function that will calculate the exponential moving average for regular intervals. I'll call this EMA. And it's going to take in two inputs, the current price and the previous exponential moving average. Let's call this U. Remember that for regular intervals, the parameter A was a constant. So let's set this A to be equal to, let's say, 0.1. And then we'll say return A times the current price P plus 1 minus A times the previous exponential moving average U. Next, we'll create some random numbers that will represent the price of a token. And then we'll calculate the EMA and then graph both of them. Let's create 100 random points. And then let's set the initial price, P0, let's say is equal to 10. Next, we'll create some random points that will represent the change in price. To do this, we'll need to call the function np.random.normal. We'll create a change in price that will deviate from 0 with having some kind of volatility. Let's call this B. And we'll create 100 random points, so n. We have not defined what b is yet, so let's say b is equal to 2. Let's assign this to a variable called delta prices is equal to. Let's see what this looks like. In Jupyter Labs, the last variable will be printed, so we can simply say delta prices, and then execute the command. Okay, and this is what this delta price will represent. You can see that it's just random numbers that deviate from 0. Sometimes it's positive and other times it's negative. Next, let's create an array of prices. Prices is equal to, and the way we're going to create it is we'll set our initial price to be equal to P0, and then we'll run a for loop, and then to this price, we'll add the delta prices. So say for dp in delta prices, we'll first append the current price to the array prices, prices.append p, and then we'll calculate the next price by saying to the current price, add this delta price, dp. Now when we add delta price, this price can be less than 0. To make sure that this price stays above or equal to 0, let's say if p is less than 0, then set p equal to 0. Okay, so that creates some random prices. Let's see what this looks like. To plot this on a graph, we'll use the plot from Matplotlib. We'll do this by typing plot, plt, dot plot prices. And then to show this, we'll say plt dot show. Execute the command. And this is what our prices will look like. If we execute again, since the numbers are generated randomly, you'll see a different graph. Okay, next, given this prices, let's calculate the exponential moving average for regular intervals, and then also plot this on the same graph. So similar to what we did over here, we'll construct the array of exponential moving averages, EMAs equals to array. And we'll initialize our EMA, let's call this U, to be equal to the initial price, P0. And then we'll run a for loop for P in prices. We'll first append the current exponential moving average to this array, emas.append U. And then we'll calculate the next exponential moving average. I'll say U is equal to EMA of P and the current U. Okay, let's also plot this. So here I'll say plt.plot EMAS. And let's also introduce some legends so that we'll know what line will represent which data. plt.legend, the first one will be price, and then the next one will be EMA. Okay, let's execute the command again. And this is what we get. The prices are these zigzag lines, and the exponential moving average is this orange line. What you can notice is that this orange line is sort of like a smoothed out version of this zigzag. And also, the price given by the EMA lags behind the actual price. For example, over here, after the price spikes and then dips, you can also see that the exponential moving average sort of spikes up a little bit and then goes down. We can also run this again to get a different graph, and this is the graph that we get. We can also play around with this A parameter. For example, instead of having it equal to 0.1, if we set it to 0.9 and then execute it, you'll see that the EMA follows the current price more tightly than before. In this video, I'll explain how the exponential moving average is calculated for irregular intervals. First, let's go over a review of how the exponential moving average is calculated for regular intervals. For example, let's say every 1 second. We'll take the moving average every 1 second. To start off with, we define two variables, P of t and M of t. P of t will be the price at time t, and M of t will be the moving average at time t. The algorithm to calculate the moving average for regular intervals works like this. We first define M of 0, so this will be the moving average at time 0 to be equal to the price at time 0. And the moving average for time t greater than 0 is defined recursively based on the moving average at previous time. We first specify a value a that is greater than or equal to 0 and less than or equal to 1. This value a will be fixed, and it will be used throughout to calculate the moving average for all time. So the exponential moving average at time t greater than 0 is defined to be a multiplied by the price at time t plus 1 minus a multiplied by the previous moving average, the moving average at time t minus 1. Okay, this is just a review of how to calculate the exponential moving average for regular intervals. Now on the blockchain, you don't have any guarantees that you'll be able to make updates every 1 second. So to find the exponential moving average, we need to figure out a way to calculate the exponential moving average for irregular intervals. For example, an update might happen 1 second, and then next it might happen 2 seconds after, and next it might happen after 3 seconds or 1 hour. So let me first define our problem. Let's say I have a price graph of a token. The horizontal axis will represent time, and time will flow from left to right. The vertical axis will represent the price of this token. The price of the token, as time passes, will go up and down, up and down. Let's say that we wanted to take the moving average at time t0, t1, t2, and so on, all the way up to tn, where the time in between any of these 2 points are irregular. So, for example, let's say that we wanted to start taking the moving average at time t0. Here, let's denote the price at p of t0. Maybe 2 seconds later, we want to recalculate the moving average at time t1. Maybe after 10 seconds later, we want to take the moving average again at time t2. This continues all the way up to tn. The time between any of these 2 points are irregular. So how do we calculate the moving average in this case? I'll start by defining a variable that represents the moving average for irregular time. Let's call this m star t. This will be the moving average with irregular intervals at time t. The algorithm to calculate the moving average for irregular intervals is similar to the one for calculating the moving average for regular intervals. We first start by initializing the moving average to the price. So let's say that we wanted to take the irregular moving average at time t0, m star t0. We set this equal to the price at time t0, p of t0. And then to calculate the moving average for time greater than t0, let's call this m star of t of I. And this will be equal to some variable a multiplied by the price at time t of I plus 1 minus some variable a again multiplied by the previous exponential moving average for irregular intervals, the one at t of I minus 1. So far this looks exactly like the equation for regular intervals. However, here's the difference. This a will not be a constant. It will be a variable depending on the time. So we'll denote this value a as a of t of I. It will be different for each time. However, one of the properties that still must be true is that a of ti must still be greater than or equal to 0 and less than or equal to 1. I'll explain later how this A of ti is chosen for each time interval. Here I'm going to show you what this equation will look like when we unpack all of the exponential moving average for all time t of I. Let's start by expanding the exponential moving average at time t of I minus 1. I'll copy this and paste it here. And then what is this equal to? Well, we can apply the definition again. We can apply this definition or m of t of I minus 1. So I'll copy this and then paste it here. What we need to do is simply replace I with I minus 1. And then replace I minus 1 with I minus 2. Okay, so this is what m of t of I minus 1 is equal to. And then we multiply this by 1 minus a of t of I. So now the equation will look like this. Okay, let's next expand this part out. Multiply the first term by 1 minus a of t of I, and then multiply the second term by 1 minus a of t of I again. What you'll notice is that this term is multiplied by 1 minus a of t of I, and then the next term is multiplied by 1 minus a of t of I, multiplied by 1 minus a of t of I minus 1. We can keep expanding this until the last term, m star of t0. And what you'll see is that the price in the past will be multiplied by these terms 1 minus a of t of I. And the last term will be multiplied by 1 minus a of t of I, multiplied by 1 minus a of t of I minus 1, all the way up to 1 minus a of t of 1. Now remember that the equation for the exponential moving average for regular intervals looked like this. Each term, as it goes further back in the past, is multiplied by a power of 1 minus a. And the last term being multiplied by 1 minus a to the power of time elapsed. And you can check for yourself that the equation for the irregular intervals will match the equation for the regular intervals when all of this a of t of I is equal to each other. Okay, this is what the equation will look like when we expand all of the terms out. Next, I'm going to explain how this a of t of I is picked. The value for a of t of I is picked so that 1 minus a of t of I will exponentially decay with the time in between t of I and t of I minus 1. For example, in Curve B2, the value of a of ti is picked so that 1 minus a of ti will have, after every interval, let's call this h. So when the time difference between the last time the exponential moving average was updated and the current time is equal to 0, then it would return a 1, and after h seconds, this value will be 0.5, and after another h seconds, this value will return half of that, so this will be 0.25. And after another h seconds, this will be half of 0.25, which will be equal to 0.125, and so on. Every h interval, the value will have. This is how 1 minus a of t is picked in Curve B2. We can also write this as a math equation. 1 minus a of t of I is equal to, the value will be half after every h seconds. Half will be 0.5. After 0 seconds, this will be equal to 1. And then after h seconds, this will be equal to 0.5. And after 2 times h seconds, this will be equal to 0.5 raised to the power of 2, which is equal to 1/4, which is equal to 0.25. And after 3 times h seconds, this will be equal to 0.5 raised to the power of 3, or 1/8, which is equal to 0.125, and so on. So we can generalize this by saying that 1 minus a of t of I is equal to the time elapsed divided by the interval h. This is equal to e raised to the natural log of 0.5 multiplied by the time elapsed divided by h. You'll see this equation being used in Curve B2 to calculate the value for 1 minus a of t of I. Let's also run a simulation for exponential moving average for irregular intervals. I'll first start by copying the code for regular intervals. Then I'll create a new cell, and then paste it here. We'll first define the half-life. This will be the time interval where the a that is used inside the exponential moving average will become halved. So let's set h equals to 4. This will mean that after 4 seconds, this value a will be 0.5, and then after 8 seconds, this will be 1/4, which is 0.25, and then after 12 seconds, this will be 1/8, which is equal to 0.125, and so on. Okay, next let's calculate the exponential moving average for irregular time intervals. For the input, we'll pass in the price, the previous exponential moving average, and the time that has elapsed, dt. What we need to do is calculate a. What we said was that 1 minus a should be equal to e raised to the power of natural log of 0.5 multiplied by the time elapsed divided by h. So solving for a, this will be a is equal to 1 minus, the exponential is calculated by using the library called math.exp. And then inside here, we'll pass in the power. The power is math.natural log of 0.5 times dt divided by h. Okay, and the rest of the code, this should be a 1. The rest of the code is the same. Okay, let's move on to plotting the points. Should have 100 points, initial price will be 10, and then we create some random delta prices, and then construct the prices. Okay, next let's calculate the EMAs. For this example, I want to show you both the regular interval and irregular interval. So we'll create an array of arrays. The first array will store the EMA for regular intervals, and the next array will store the EMA for irregular intervals. And then we'll start by calculating the EMA for regular intervals, which we've already seen how to do. What we'll need to do is append to EMAs of 0 the EMA for regular intervals. And now this function EMA takes in delta time. So for the delta time, all we have to do is pass in 1. Okay, next, let's construct the EMAs for irregular intervals. We'll create a variable called t, which will represent the current time. And then we'll create an array called t of s, which will represent the times when the EMA was taken. And then we'll initialize the EMA to be equal to the initial price, p of 0. And then we'll run a while loop. While the time t is less than n, we'll first append the timestamp, let's say ts.append t. And then we'll also append the EMA. EMA s of 1, which will represent the EMA for irregular intervals, append the current EMA. And then let's simulate some random time interval. Let's say dt is equal to mp.random rand_int between the time 1 and let's say 2 times h. Then we add this to t, the current time, t plus equals dt. And if this time has not exceeded the last time, n, let's calculate the EMA. Let's say if t is less than n, then let's get the price. P is equal to prices of t, and then we'll recalculate the exponential moving average. U is equal to EMA of p, the current exponential moving average, and dt, the time elapsed. Okay, let's now plot these. So we'll plot the prices, and then the EMA for regular interval. And then I'll also put a marker with a plus. And then next we'll plot the plot for irregular intervals, plt.plot EMAs of 1, having the marker equals, let's say, lowercase o. And then we also modify the legends, regular interval and irregular interval. Okay, and let's now see what the graph will look like. Okay, I made a mistake over here. So going back up, this P1 is not defined, should be P0. Okay, let's try executing the code again. I also made a mistake for how to graph the EMA for irregular intervals. Here we'll need to pass in the timestamp that corresponds to the EMAs. So here I'll type TS. TS is the array that holds the timestamp when the EMA for irregular intervals will take in. Okay, let's try executing again. Okay, and this is what we get. The graph in blue represents the price over time. The graph in orange represents the EMA for regular intervals, and the time that the EMA is calculated is represented by these plus signs. And then finally, we have the EMA for irregular intervals, which is shown in green. The green dots that you see over here represents the time when this EMA was calculated. And as you can see, the interval between these points are irregular. Here they're very close, and over here they're very far. Next it's very close again, and then next it's a little bit further away. We can also run the simulation again to get a different graph, and this is what we get. So these are some simulations of the EMA using Python. In the math that I showed you so far about exponential moving average for irregular intervals, this is the equation that I introduced. However, inside the code of Curve B2 AMM, the equation looks slightly different. what it looks like is going to be, let's rename this to say m tick of TI. If you write up the code as an equation, you'll see that this 1 minus a of TI and this a of TI are switched. So this is what the code will look like. Now to avoid confusion, I'm going to rename this variable. However, here I'm going to quickly explain why this is not a problem. These two equations are basically the same thing. And to see this, all we have to do is substitute a of TI with 1 minus a tick of TI. So we set 1 minus a tick of TI equal to a of TI. So now you can see that this term and these terms are the same. Okay, but how do we replace 1 minus a of TI then? Well, we can do simple algebra. All we have to do is say we minus a of TI from both sides of the equation. So this will bring a of TI over to the left. And then we add a tick of TI to both sides of the equation. And this will bring a tick of TI to the right side of the equation. So these are the two equations that we have. And as you can see, these substitution, the first term will be substituted by 1 minus a tick of TI that you see over here. And the second term, 1 minus a of TI, will be replaced by a tick of TI. So you can see that these two equations are basically the same. Okay, but how about this property? Does this property still hold? When we picked a of TI, we said that this must be greater than or equal to 0 and less than or equal to 1. So when we make this substitution rule, does it still apply? Well, let's check. We know that this is equal to a of TI. So we can say that this expression will also be less than or equal to 1. From here, I'm going to remove this a of TI, and we will get this. And now we can use simple algebra. We minus 1, so this will become a minus 1. This will disappear, and 1 minus 1 will be 0. And then we multiply all of this inequality by minus 1, so this will become a 1, and this minus 1 will disappear, and this 0 will stay the same. Since we multiply by minus 1, the inequalities will flip. Or I can just switch these numbers around. 0 will come over here, and 1 will come over here. From this equation, it follows that this variable that's been substituted, a tick of TI, will still be between the range 0 and 1. Now also in the math that I show you, this is the equation that we use to determine the value for a of TI. But inside the code for Curve betwee AMM, what you'll see is that this last expression, e raised to the ln of 0.5 divided by the time elapsed divided by some time interval h, will be set to this variable a tick of TI. Inside the code, this a tick of TI is named as alpha. Okay, but is this equation true? Well, from this substitution rule that we found out, we noticed that 1 minus a of TI is equal to a tick of TI. So this equation also holds. So in summary, when I explain the math for exponential moving average for irregular intervals, we use this equation and this equation. However, inside the code for Curve betwee AMM, the equation that is being used is this equation and this equation. Alright, we've seen the math for exponential moving average for irregular intervals. Let's look at the code inside the Curve betwee AMM to see how it's actually implemented. There are two places where the logic for calculating the exponential moving average is used. One of them is an external function called price-repegging, and then the other part is inside an internal function called tweak price. In this video, let's take a look at the function price-repegging. For the input, it's going to take in a parameter called k. This input represents the index of the coin minus 1. For example, if you wanted to find the exponential moving average of coin 1, then for k, you will pass in 0. And if you wanted to find the exponential moving average of coin 2, then here you'll pass in 1. And the output is the exponential moving average of that coin. Let's take a look at the code. First, it unpacks some state variables. Here, the price-repegging variable will represent the exponential moving average. And then we have the price scale, the last time the price were updated, and if the last time the price were updated is less than now, then it will calculate the new exponential moving average. First, it will unpack the last prices from a state variable called last prices packed. And then it will get a variable called MA time, moving average time. And then next it calculates this alpha. This alpha is calculated by taking e raised to the power of time elapsed block.timestamp minus the last time that the price were updated, scales it up by 10 to the 18, and then divides by MA time. Inside the math that we saw, we said that alpha is equal to e raised to the ln of 0.5 multiplied by the time elapsed divided by h. Since ln of 0.5 is a constant, this is included in this variable ma time. So ma time will be equal to the half-life divided by ln of 2. You can do a quick algebra to check that ln of 0.5 is equal to ln of 1/2, which is equal to minus ln of 2. And also notice that there is a minus over here. This minus comes from the fact that ln of 0.5 is equal to minus ln of 2. To cancel out this minus, we put a minus in front. Okay, so this is how alpha is calculated. And then the last step is to calculate the new exponential moving average. Remember that exponential moving average was basically calculated by taking the last price multiplied by some scale, 1 minus alpha, and then to this we add alpha multiplied by the previous exponential moving average. But here the code is a little bit more complex. It's taking the minimum of last price with 2 times the price scale. Basically what it's doing here is that it's making sure that the last price doesn't change too significantly from the price scale. Okay, so this is how the exponential moving average is calculated inside Curve B2AMM. You'll see this code again inside the function tweak price. Here I want to explain the relationship between external functions, the internal function tweak price, and the state variables virtual price and the variable d. So the user has options to call the function exchange, add liquidity, remove liquidity, or remove liquidity one coin. In all of the case except for calling the function remove liquidity, it will call an internal function called tweak price. This function, as the name suggests, is called when the Curve B2AMM might need to change its price and repeg. And the price would change when either the function exchange, add liquidity, or remove liquidity one coin is called. Add liquidity because we can add single-sided liquidity, which might change the internal price of a token. Remove liquidity one coin. Again, this will change the ratio of the token balances, so this might have an effect of changing the internal price. So this is why the function tweak price is called when the function exchange, add liquidity, or remove liquidity one coin is called. But how about remove liquidity? Well, when the function remove liquidity is called, it does not change the price, since all of the tokens are withdrawn so that the internal price remains the same. When the function tweak price is called, it will need to make a decision whether to repeg or keep the peg the same. When it repegs, this will affect the virtual price and the variable d. Well, first it's going to affect the value for d, because when we repeg, we're trying to find this new value for d, the new center of liquidity. And the virtual price is calculated based on this value d. So when this value d changes, the virtual price also is affected. And the other factor that will affect this d value is when the function exchange, add liquidity, or remove liquidity one coin is called to collect some fees. Swap fee is collected when the function exchange is called, and imbalance fee is collected when either add liquidity or remove liquidity one coin is called. When the fees are collected, this will increase the liquidity, so this value d will also increase, which will affect the virtual price. The internal function tweak price is called to repeg the price scale. Before we do a cold walkthrough of this function, here I want to quickly outline what the function does. So the function tweak price, it takes in several inputs, but the two inputs that I want to highlight here are _xp and the new value for d. The first thing it does is that if the last price that was updated is less than now, then it will update a state variable called price oracle. This will store the exponential moving average of the tokens. Next, it will calculate and update the last prices. Then it will initialize an array called xp, setting xp a byte to be equal to d over n times the price scale of byte. This number represents when all of the transformed token balances are equal to each other. It also represents the center of where liquidity is currently concentrated. Next, it initializes a variable called xcp profit equal to 1. The naming is a little bit weird. The way to remember this is x and cp will be constant product, and then profit. This variable represents the profit that this pool has made from collecting fees. And then it will also initialize virtual price equal to 1. And then it will get the current virtual price that is stored in a state variable. This is labeled as old virtual price. And if this old virtual price is greater than 0, then it will first calculate a variable called xcp. This is equal to the product of xp remember xp was this number, and then taking the nth root. And what this represents is the pool value. This is exactly equal to the equation of the pool value, and then it calculates the new virtual price. The virtual price is defined to be XCP divided by the total supply, where total supply is the total supply of the LP tokens. So virtual price will represent how much LP shares is worth. And then it does this weird thing where it updates XCP profit by taking the previous XCP profit and then taking the ratio of the new virtual price that was just calculated and the current virtual price, which is stored inside the state variable. So I said earlier that XCP profit represents the profit only that comes from collecting fees. And this is the code that makes sure that XCP profit represents the profit that the pool has made only from fees. I'll explain how this code works in another video, so let's move on. And then next it updates the XCP profit. And then if new virtual price is greater than half of the XCP profit plus some extra profit, this extra profit is a setting inside the pool contract. So if the new virtual price is greater than half of the XCP profit plus some buffer, then it's going to try to make a decision whether it needs to repeg or not. And it does this by first calculating the distance between the exponential moving average and the current price scale. Price scale will represent where the current peg is, where the liquidity is currently concentrated. So compare this peg with the exponential moving average and calculate the distance. Inside the code, this distance is named as norm. And then if this distance is large enough, then now Curve has to decide whether it can repeg or to keep the peg the same. And to decide whether to repeg or not, it first needs to calculate the new peg, where it's going to repeg to. So it's going to adjust the current price scale to a new price scale. Let's call this P new. Now it's a little bit confusing here what it's doing. What it's doing is it's using the array called xpaby to mean something else. It's going to set xpaby to be equal to the token balances, xpaby, multiplied by the new price scale. And since this xpaby represents the transform balances, to cancel out the previous price scale, it divides by the price scale. And then store this result into the array xpaby. So remember up here that xpaby represented this. And now it's storing something else. So this is a little bit confusing. And then using this xpaby that stores the new transform balance with the new price scale, it calculates the new value for D. What it's doing is it's saying, given these new transform balances, what is the value of D that will satisfy the Curve B2 equation with these new transform balances? And then after it calculates the new D, now it's going to use this XP array again to store something else. What it's going to store is this new D divided by N times the new price scale by. So now what this will represent is a new center of where liquidity might be concentrated, if the liquidity was to be concentrated at this new price scale. Once this new xpaby is calculated, next it will calculate the new virtual price. Now, remember back over here that the way that the virtual price is calculated is we first calculate this XCP by taking the product of XP and then taking the nth root. And then the new virtual price is calculated by taking this XCP dividing by the total supply. And here it's the same. Using this new XP, it will calculate XCP, and then using XCP, it will calculate the new virtual price by dividing it by the total supply. So now that we know what the new virtual price is, the final step is to whether to decide to repeg or not. If this new virtual price is still greater than half of XCP profit, then update the state variable D to be this new D that was calculated above, update the virtual price to be the new virtual price that was calculated over here, update the price scale to this new P new, and then end the execution of this function. Otherwise, so if this new virtual price is not greater than half of the profit that was generated, then what it's going to do is update D and then update the virtual price. So that ends the code outline for the function tweak price. The function tweak price is one of the most complex code inside the contract Curve Crypto Optimized WEF. This function is called when the price might have changed and the price scale might have to be repegged. The parameter that this function takes is a gamma, xp, new d, and k0 preb. A gamma is the parameter A and gamma, XP will be the transform balances, new D will be the new value for the D, and K0 prep, this is the number that is used as an initial guess to calculate the new D. Okay, let's take a look at the function body. The first thing it does is unpack some state variables. Rebalancing parameters, price oracle, this will store the exponential moving average, last prices, packed price scales, price scale, and then further on it caches the state variables, total supply, XCP profit. This variable represents the profit that this pool has collected from fees. And then we have the virtual price. The virtual price will be the value of each LP shares. And the value of this LP shares will increase when fees are collected. So what's the difference between virtual price and XCP profit? The difference is XCP profit only accounts for the growth from collected fees. On the other hand, virtual price also includes the fees, and it's also affected by when repeg happens. When the price scale updates, this virtual price might go up or it might go down, whereas XCP profit is not affected by repegs. Moving on, it also caches the last prices timestamp. And if this last prices timestamp is less than now, then it will update the exponential moving average. So here we see the code that will calculate the alpha. This was already discussed when we looked at the code for the price oracle. And then it will update for each token the exponential moving average, and then store the exponential moving average in the state variable price oracle packed, updates the last price timestamp. Okay, so moving on. Next, it calculates the new value for D. First, it initializes it as a new D, which is passed from the input, and if this new D is equal to 0, it will recalculate it. This new D will be equal to 0 when the function exchange is called. Okay, so once we have this D unadjusted, the next thing it does is it calculates the last prices by calling a function called getP inside the math library contract. And then next it stores the last prices. And then moving on, the next part of the code will calculate D divided by N times the price scale. First it initializes an array called XP. For the first token, the price scale is always equal to 1, so XP of 0 will simply be D divided by N. And for the rest of the token, we calculate D divided by N times the price scale. Okay, the next part of the code deals with updating the XCP profit. First, it initializes the XCP profit to be equal to 1, and the virtual price also equal to 1. If the old virtual price, this old virtual price is the state variable that was cached over here. So if this current virtual price that is stored in the state variable is greater than 0, then it will first calculate XCP by taking the geometric mean of XP. So XP will be an array holding these values, and then the geometric mean will multiply all of these elements and then take the nth root. So this XCP will be the calculation of the pool value. Take the pool value divided by the total supply, and that will give us the virtual price. Okay, and the next part of the code is to update XCP profit. XCP profit is defined to be the old XCP profit multiplied by the virtual price that was calculated just now, divided by the virtual price that is stored in the state variable. Consider the ratio of virtual price and old virtual price. This will give us a ratio of how the virtual price either increased or decreased. And old XCP profit will also hold the previous accumulated rates of virtual price growth or loss. So what this is doing is it's accumulating all of the increase or decrease in the ratio of virtual prices. And when we multiply this by the initial virtual price, which is equal to 1, this will give us the growth in virtual price from the initial virtual price. Now for more details on how this XCP profit works, I put some comments in here that you can follow along, and I'll also explain this comments in the next video. So let's move on. The next part of the code says that if future A gamma time is less than blocked out timestamp, this means that A and gamma are not going to update, then make sure that the virtual price that was calculated currently is greater than the virtual price that is stored in the state variable. And then it updates the XCP profit. The next part of the code deals with rebalancing the liquidity if there is enough profit. So here's the logic. If the current virtual price that was calculated multiplied by some number is greater than some expression over here, then it will execute the rest of the code. You can simplify this part of the code, and what it would say is that if the virtual price is greater than 1 plus XCP profit divided by 2 plus some rebalancing parameters, which stores allowed extra profit. And what would this look like geometrically? So let's say that the XCP profit is somewhere over here, and then the number 1 will be over here. 1 plus XCP profit divided by 2, let's say, will be here, the midpoint of XCP profit and 1. And the condition is virtual price greater than 1 plus XCP profit divided by 2 plus some allowed extra profit. For simplicity, let's say that this allowed extra profit is equal to 0. Then what would this condition mean? Well, this would mean that the virtual price must be greater than the midpoint between 1 and XCP profit. So if the virtual price satisfies this condition, let's see what happens. The first thing it does is it calculates the distance between the current price scale and the exponential moving average. And this distance will be stored in a variable called norm. So if you take a look at over here, and you can check the code inside the loop for yourself, you'll find out that this norm will turn out to be the square root of the sum of the absolute value of 1 minus r, where r is the ratio of the price oracle divided by the price scale. Next, it creates a variable called adjustment step. And if this norm is greater than the adjustment step, then Curve B2 will try to update the price scale. In other words, it would try to repeg. To repeg, it first creates a price scale that it might repeg to. After it calculates the new price scale to repeg to, then it uses the array XP to store the new transform balances at the new price scale. And then after it calculates this new transform balance, it will calculate the new value for D. And then it does some checks, and then it reuses the XP array to mean something else. This time it will mean D divided by N times the price scale. Using this XP, it will calculate the new virtual price. However, it's using the old virtual price to mean the new virtual price. And if this new virtual price that was just calculated using the new price scale satisfies this condition, and again this condition turns out to be that new virtual price is greater than 1 plus XCP profit divided by 2. If this condition is true, it will store the new D that was calculated into the state variable, it will store the new virtual price, and it will store the new price scale. And then the function ends here. Otherwise, the other condition is if virtual price is less than or equal to 1 plus XCP profit divided by 2 plus allowed extra profit. So if this virtual price is still below this midpoint, assuming that allowed extra profit is equal to 0, then what it's going to do is it's simply going to update the value for D, and then also the virtual price, and then return the packed price scales. So that ends the code walkthrough for the function tweak price. When the function tweak price is called, it updates a state variable called XCP profit. The way it is updated is by taking the current XCP profit. This is stored in a variable called old XCP profit. Multiply this by the virtual price that was just calculated, and then divide by the current virtual price that is stored in the state variable. This is called old virtual price. To understand how the XCP profit keeps track of the growth or decrease in the pool only from collecting swap fees, you'll start by naming some variables. Let's say that B state of I is the virtual price stored in the state variable at time I, and you'll call B calc of I to be the virtual price calculated at time I. Now let's go back to the equation. XCP profit is equal to the old XCP profit multiplied by the calculated virtual price divided by the old virtual price. Now old XCP profit is initialized to be 1. So with that said, let's now rewrite what XCP profit will be equal to on the first iteration. When the function tweak price is called for the first time, XCP profit will be equal to 1 multiplied by B calc of 0 divided by B state of 0. The next time the function tweak price is called, since now the old XCP profit will store the previous XCP profit, which is equal to 1 multiplied by B calc of 0 divided by B state of 0. When we do this calculation again, we multiply the previous XCP profit by the current virtual price that was calculated at time 1, divide by the virtual price stored in the state variable at time 1. Do this again when the function tweak price is called, and to the previous value of XCP profit, we multiply the new calculation of virtual price at time 2, divide by the virtual price stored at time 2. We can keep going on in this manner And let's imagine that XCP profit was updated n+1 times. The last update will be multiply the previous XCP profit by b calc of n divided by b state of n. And this is what XCP profit will store if this XCP profit was updated n+1 times. Now, to get a better feeling of what these multiplications and divisions are doing, let's consider a simple case. And before we do that, I'll mention here that at the end of the function tweak price, the virtual price state variable will be updated to be the current calculation. We can represent this using our labels that b state of I will be equal to b calc of I. And this is only updated at the end of the function tweak price. At the beginning, when the function tweak price is called, this may not be true. The calculation for the virtual price at time I might not be equal to the virtual price state variable stored at time I. However, at the end of the calculation, the new state variable is updated to be equal to the calculation. Okay, so let's now consider a simple case. Let's say that in between the function calls to tweak price, the state variable that is stored in the virtual price does not change. We can write this as before the function tweak price is called, b state of I is equal to b state of I minus 1. But however, we also mentioned that at the end of the function tweak price, b state of I minus 1 will hold the calculation b calc of I minus 1. Putting these together, we can say that b state of I is equal to b calc of I minus 1. Right before the function tweak price applies this update to the XCP profit. Now when we assume that b state of I is equal to b calc of I minus 1, a lot of the numbers cancel out. The calculation made at time 0 will cancel out with the state at time 1. The calculation made at time 1 will cancel out with the state variable at time 2. Calculation made at time 2 will cancel out with the state variable at time 3. And so on, we go all the way down to state variable at time n. All of these will cancel out and we're left with the calculation at time n and the state variable at time 0. This reduces to a simple equation. XCP profit is equal to the initial XCP profit, 1, multiplied by the calculation made at time n divided by the state variable stored at time 0. Now this equation looks like it represents the growth rate of virtual price calculated at time n, comparing it with the virtual price at time 0. However, since the initial virtual price is equal to 1, and you can think about it as this equation being multiplied by 1, the initial virtual price, and we get that XCP profit represents the growth in virtual price from time 0. Since this part of the code is executed before a repeg, this equation represents the growth in virtual price from time 0, only accounting for the growth from collecting fees, or the decrease in virtual price when the admin collects the fees. So we looked at a simple example, but in practice, almost all of the time, the state variable at time I will not be equal to the calculation made at time I minus 1. So we get that the XCP profit is represented by this long multiplication and divisions. The internal function claim admin fees is called when the functions add liquidity, remove liquidity, or remove liquidity while going is called. This function will claim some of the fees that were collected and then mint LP shares for the amount of fees that it claimed. Since it's going to mint LP shares, this will increase the total supply, which will affect the virtual price. Claiming admin fees will also affect the state variable D, and also affects the state variables that are used to keep track of the growth of the pool. These two state variables are XCP profit and the XCP profit after the last time claim admin fees was called. This is stored in XCP profit A. So these are the external functions that call into the internal function claim admin fees, and these are some of the state variables that are updated when the function claim admin fees is called. Let's do the code walkthrough for the function claim admin fees. This function is called to claim admin fees, and the fee that is collected by admin is used to mint some LP shares for the admin. In this way, the admin does not have to transfer the tokens out and then put it back in to mint LP shares for himself. Inside the function, it first calculates A and gamma, and then caches some state variable, XCP profit A, and then total supply. XCP profit A is a state variable that is updated every time the function claim admin fee is called. And at the end of this function, you'll see that this XCP profit A is updated to be the current XCP profit. And also you'll see later that when we take the difference of the current XCP profit and the last time XCP profit was stored, XCP profit A, then this difference will represent the profit or the growth in XCP profit. Okay, moving on. if XCP profit is less than or equal to the last time XCP profit was stored, then we simply return from this function. Next, it syncs up the token balances to the state variable balances. And you can see here that balances by is equal to the token balance of this contract. And then it caches the state variable virtual price. And then next it calculates the amount of fees that the admin is going to claim. The equation is given by taking the XCP profit minus XCP profit A multiplied by the percentage determined by admin fee divided by 10 to the 10. Now you also see that it's also dividing by 2. So what is going on over here? Well, above here, I've created a diagram to show what is going on inside here. So let's say XCP profit is here. And let's also say XCP profit A is over here. This height will represent the profit, the difference between XCP profit and XCP profit A. The admin fee is hard-coded as 50%. So 50% of this difference, let's say, will be half of the height. So let's say it's over here. The comment over here says that half of the profit goes to rebalancing the pool. So half of this profit, let's say this part, goes to rebalancing the pool. So the actual profit that can be claimed will be this part. And then half of this will go to the admin. So the admin is going to get 1/4 of the difference between XCP profit and XCP profit A. And this is what this 2 is doing over here. Here's the calculation that is shown here. And if you simplify the equation, you'll see that this turns out to be XCP profit minus XCP profit A times 1/4, which is what we just discussed in this diagram. This 1/4 part is the admin's profit to be claimed. Okay, and then moving on, if the address of the receiver is not the empty address, and if fees is greater than 0, then next it calculates the fraction of LP shares to mint to the admin. And this is the calculation that is done to calculate the amount of LP shares to mint. It's taking the virtual price, multiplying by 10 to the 18, and then dividing by the current virtual price minus the fees minus 10 to the 18. So what's going on over here? Well, here is the explanation. Let's say that B will be equal to the virtual price, F will be equal to the fees that was just calculated above, capital T will be total supply, and Q will represent this fraction. You'll see later that this will represent the percentage of growth of virtual price from B minus F to B. And imagine that the admin increased the virtual price from B minus F to B. In proportion to this, we're going to mint LP shares. Let's call this ratio the ratio of increase from B minus F to B equal to Q. Then the equation that we need to solve is total supply. The growth in total supply will be T times 1 plus Q divided by the previous total supply, T. And the virtual price increased from B minus F to B. And then solving for Q will give us the amount of LP shares to mint. This is a simple algebra, and you'll find out that Q is equal to B divided by B minus F minus 1, which is the equation that you see over here. So once this percentage of the growth in virtual price is calculated, it will mint the amount of shares relative to this growth to the admin. And that is what you see over here. Okay, and then on the next line, it deducts XCP profit, fees times 2. Now remember that fees represents 1/4, so just this part of the whole profit. So by multiplying by 2, what you're going to get is the profit, half of the profit, which is the profit divided by 2. Now I'm not entirely sure why it is deducting this much amount. Since the admin only claimed 1/4, I'm not sure why it is deducting half of the profit. So anyways, moving on, it next updates the state variable XCP profit, logs the event, and then also calculates the variable D, and then stores it in the state variable. And then at the end, it updates the virtual price, and then the XCP profit A is set to the XCP profit that was just calculated over here. That completes the code walkthrough for the function claim admin fees. The spot price of an AMN such as the constant sum, constant product, curve B1, and curve B2 can be calculated by taking the derivative of their curves. Once we calculate the derivative, we can calculate the spot price by feeding in the token amount into the derivative. And this is the relationship between token X in the pool and the spot price of token X. For the constant sum, the price is always equal to 1. The spot price of constant product AMM is shown in blue. The spot price of curve B1 is shown in orange, and the spot price of curve B2 is shown in green. I'm going to use the equation of the constant product AMM to illustrate how the derivative of a AMM represents the spot price. In orange, you see the curve of the constant product AMM, and blue represents the derivative of this constant product at this point. Let's say that we do a trade for some amount of token X, put in token X, and we get back out token Y. The resulting token balances is represented here. When you take this difference, dy divided by dx, this will give us the exchange rate of the trade. The spot price of the AMM is simply the exchange rate when we make this dx really small. So as we decrease the amount of token X that is swapped in, you can see that this slope approached the slope of this blue curve, which represents the derivative at this point. So this is the intuition for why taking the derivative of an AMM will give us the spot price. The spot price basically tells us that if we were to do a small trade, then what is the exchange rate? And this is calculated by taking the derivative of the AMM. Now the derivative of the constant sum and the constant product is easy to calculate. This is because we can isolate the variable y from the equation. For example, from the equation of constant product AMM, x times y equals d over 2 square, we can solve for y by bringing this x over to the right. And then taking the derivative will give us the spot price of a constant product AMM. However, this is not the case for curve B1 and curve B2. Take a look at the equation for curve B1. The equation is complex, and there's no easy way to bring y over to one side of the equation and everything else to the other side of the equation. These type of equations are called implicit functions. However, we can still find the derivative of these complex equations. The technique that is used to calculate the derivative of an AMM is called implicit differentiation. The derivative of AMM is dy dx, and under certain conditions, we can calculate this derivative by taking the partial derivative with respect to x, and then dividing it by the partial derivative with respect to y. For example, if the function was x times y equals L squared, the constant product AMM equation, then taking the partial derivative with respect to x, you'll get y on top, and then taking the partial derivative with respect to y, you'll get an x. So the spot price of a constant product AMM is minus y divided by x, which agrees with what we saw in the example. So now back to this graph. In this video, I'm going to quickly explain how I use Python to calculate the derivative of curve B1 and curve B2. The file that I'll show you in this example is called AMM dydx. And first, you'll need to install all of these Python dependencies. SymPy is used to calculate the partial derivatives. NumPy is used for math calculations. Matplotlib used to graph the curves. And SciPy is also used for calculation of the AMMs. The first thing that I did was use SymPy to construct the equation for curve B1. And then once the equation is constructed, I used the SymPy to calculate the partial derivative of this curve B1 equation with respect to x and also with respect to y. And then using the implicit differentiation, the derivative of the AMM, dy dx, is given by minus df dx divided by df dy. And printing this out, you'll get this equation. And then I did the same for curve B2's equation. Construct the curve B2's equation using SymPy, calculate the derivative, and then print it out over here. And you can see over here that the curve B2's derivative is complex and really long. Next, what we're going to do is take these equations, so these represent the derivative of the AMM, and then we're going to plot them. So scrolling all the way down, here first I define some functions for the constant product, the derivative of the constant product, curve B1, the derivative of curve B1, curve B2, and the derivative of curve B2. Next, I create some points on the x-axis. This will represent the token balance of token x. And for each x from here, we calculate the y value for each AMM. For a constant product, there's an explicit formula to calculate the y given x. However, for curve B1 and curve B2, there's no explicit formula. So here we use an advanced math library called fsolve from SciPy. What this function will do is it will approximate the value for y given x. So we get the points x and y for each AMM. And then next, taking these x and y, we calculate the derivative. The derivative of constant product, curve B1 and curve B2. Once you have the derivative, we plot this, and this is the graph that you'll get, which represents the value of the derivative for each x. And what the derivative represents is the spot price of the AMM.